Okay, let's start settling down. It looks like you all had a fun night. You're all 5 minutes late, so let's try to stick to schedule as far as possible, as much as fun as we are having. Okay, so we are ready to get started today. So yesterday we heard all about thermonuclear explosions. Turns out that Kilonovae, which you'll all hear about today, turn out to be somewhat very similar class of objects. And we'll have our first lecture by Brian again, who'll be telling us about a lot of the theory of our process powered explosions. I had two announcements before that. The first is that all the modules for the afternoon should now be on the GitHub. So you should be all set to just sync it to GitHub, and I'll be running the modules today afternoon, and we'll have two more in the next couple of days. The second more major announcement is that, so we've had a slight change in schedule for Friday. One of our speakers is unable to lecture on Friday due to some unforeseen circumstances. So what we will do is that, so we had Jeno Sokolowski scheduled for the morning and Mike Shara for the second session. So we'll just have Mike's lecture at 9 in the morning from 9 to 10:30. So Mike will be covering both the theory and observational aspects of nova eruptions. But because we have this additional slot available now, we tried to put in something fun for you all, which is that, and this is based on some feedback I heard from some of you, which is, for the second session from 11 to 12:30, we would like to hear from you, which is that what we will try to do is that during those 90 minutes, we're about 30 students at the school. I'll just send around a Google slide deck where you get to put exactly one slide, nothing more. And you get 2 minutes to speak about what are you trying to do in your research? How is LSST useful for it? And bonus points if you can tell us how the school enriches your experience. In New York, we do this thing called the Astrofest at the start of every academic year, where the idea is that we do this similar format presentation from everyone in the community. So the idea is that we want to hear from you about what your plans are and how you hope to use LSST discoveries or data, whatever you like. So I will send around the Google Slides link shortly. Please upload one slide before Friday morning, so we can we'll just walk through those slides in the session from 11 to 12:30. Okay, good. Any questions about that? Yes.
I will not be here on Friday, but just as a former student of things like this, if you put your photo and your email on your slide, then we all can find each other later, like 6 months from now, like, oh, I had this great conversation with this other student, I'm forgetting their name. Yeah, so assuming the slides are going to be posted.
Yes. All right. I guess so. That's it. Over to you, Brian.
Okay. Thanks. Everyone had a lot of fun last night. Back to the grind today. I'm going to build on the beautiful lecture by Rem on radioactivity and talk a little bit today about kilonova like transients, so those powered by the decay of our process nuclei and their connection to heavy element nucleosynthesis. I really like this image because it came from an article that was written in Quantum magazine before the 2017 merger, where some of us that had been sort of thinking a lot about mergers were sort of pushing up against the traditionalists who were thinking about supernova. And so it's an interesting snapshot into what the community's thoughts were about whether mergers could be sources of these elements. So I encourage you to go and find it. And I really love this illustration, which is one of the Simons Foundation publications. Okay, so when I was in grad school in the mid 2000s, if you opened up a textbook, and this is sort of what the chart of the periodic table would say in terms of where various elements come from, the lightest elements from the Big Bang. The intermediate mass elements, of course, are produced in different types of stars, low mass stars, exploding supernova. And then as we sort of got above the iron group, even though we don't actually know where these elements come from, we know where half of them come from for sure, which is the S process. But it would sort of get a little murkier, but nevertheless, people would say they come from supernova, which makes a lot of sense, as we'll talk about. The only way to form these heavy elements is by capturing neutrons on lighter elements, and supernova are a natural place to go looking for neutrons. But I always start almost all my talks, whether public or colloquia, by just sort of saying this is, one of the goals of the nuclear astrophysics program is really just to figure out where and when all these elements were produced. And I always also like showing, I should have put up the new JWST image, but I always show this image of Cassia. It's amazing. We can resolve these supernova remnants and see these exploding stars. And this may have been the last naked eye supernova in our galaxy. We had been around in the late 1600s. And I think it's remarkable that we can go out and actually directly see, the imprints through spectra, or even in this case, resolved spectra of individual elements, in this case, emitting X-ray lines. And so it's very obvious to us, it's very clear where these lighter elements come from, and this give rise to this famous Carl Sagan quote you've heard about. But as I said, as you get to the bottom of the periodic table, things get a little murkier. To produce these elements, the Coulomb barrier becomes prohibitive. It's not energetically favorable anymore in terms of nuclear statistical equilibrium to form these nuclei. You need rather extreme conditions, but nevertheless, these are precious metals and uranium and plutonium, and you can imagine that our society would have evolved very differently if these elements existed in different abundances on the Earth than they do. So, it's still a worthwhile task to try to figure out where all these elements are produced. So this is sort of the abundances of the solar system elements. This is in number as a function of their mass. I'll go into this in a little bit more detail, of course, but you have these sort of two sets of abundance peaks. All the elements heavier than iron are produced through capturing neutrons on lighter, what we call seed nuclei in the iron group area. And if you capture seeds very slowly compared to the beta decay time scale that Rem discussed, then you can produce what we call an S process, slow capture process. And we think that this occurs in AGB stars between the helium and the hydrogen burning shell. There are ways to make neutrons. You capture protons onto carbon that is formed in the helium shell, and then those capture helium, you can emit a neutron, and then you have neutrons sort of bathed in the iron nuclei that exist in the AGB star, and there are ways people believe, and we actually see S process elements in the atmospheres of AGB stars, so there's quite strong evidence that they come from AGB stars. But those that are produced, the other abundance peaks, the xenon peak at 130 and 195, the platinum peak. There's another R process peak around here, around mass 90. It sort of blurs in with the S process one. These are through the rapid neutron capture process, and we know the site of these is unknown. We know it must be something explosive because we need a huge flux of neutrons to be able to capture much faster than beta decay timescales. There are some clues if you look at metal poor stars, if you look at the abundances, some of the oldest stars in our galaxy, which have only experienced a few pollution events, so they've only been polluted by a few R process events, whatever those are. And this is just showing some examples of their abundances measured, and then you can show for comparison the solar system pattern with these solid lines. What you see is it's quite remarkable for many of these old metal poor stars. At the heaviest R process elements above 756, they have remarkably similar patterns to the solar system. So even though they've been polluted by just a couple events, you'd expect, those events were slightly different and they would produce different abundance patterns. You get remarkably robust abundance patterns in the heaviers. But as you go to the lighter R process elements below the second peak, you see more sort of star to star scatter. And so this is an interesting clue. It suggests a fairly robust process for producing the heavies, but maybe more diversity in the lighter R process elements. There's of course been a lot more work on this since this paper. So I always ask, okay, well, again, getting back to the R process, how do you turn a fairly common element you can create inside a star or a type 1a supernova or anything where you heat up matter hot enough, as we discussed, it wants to become nickel 56 and iron. How do you make gold from that? Well, again, the solution eluded the early alchemists, but you just bombard an iron nucleus at a very high rate with neutrons, faster than it can beta decay, and you build up this element, which is on the unstable side of the valley of stability, as Rem discussed, and then as it decays back, it will form now a heavier isotope or a heavier element of gold. Okay, so and of course these heavier elements have more neutrons than protons. So you need the trick is, where do I get this huge abundance of neutrons in nature? And a natural place to go is a neutron star. We see the one in the Casset in the center here. And the most natural, when supernova explode, of course, you are ejecting some neutron-rich material into space, but it turns out that it's very hard to get that material to be very neutron-rich because of the very strong fluxes of neutrinos that are coming out of the newly formed neutron star. They tend to want to eject roughly equal number of neutrons and protons. It's hard to get highly neutron-rich matter out of an ordinary spherically symmetric core collapse supernova. But an obvious place is just to smash two neutron stars together. And to do this, you need them to be able to collide with each other. And that, unless you have very fine-tuned something shooting them together, very fine-tuned, you need to bring them together through gravitational waves. And we probably all know this, but you can calculate in post-Newtonian order the rate at which the orbital period shrinks due to the emission of gravitational waves, for example, for two equal mass neutron stars of mass m and some separation. And this merger, this shrinkage increases in time as they get closer together. It's more powerful, so you get this sort of chirp gravitational wave signal you've presumably all seen, where the gravitational waves have twice the orbital frequency of the star, and it will go up in frequency and amplitude until they collide at the end. So you hear it audibly, the chirp. And of course, you're certainly all aware that we did actually get a chance to see one of these many years ago now, 8 years ago, something like that, in 170817. And one of the remarkable things about this particular merger, I think, is that LIGO doesn't measure the individual masses of the two objects very well, but they do measure the chirp mass. And as long as the mass ratio is not terribly different than unity, it's actually a pretty good proxy for the total mass of the binary. So they actually measure the total mass pretty well, and it's 2.7 solar masses roughly. And this is actually, if you look at almost all the binary neutron star in our galaxy that will merge within a Hubble time, it also has roughly this mass. And they're also roughly equal mass binaries in our galaxy. They're sort of roughly equal neutron stars. So if I had to guess, I would say these were probably two very close to being the same mass neutron stars. And what this also means is that this event might be sort of representative of the type of mergers that have happened or do happen in the Milky Way. And so we might be able to learn something about what this event produced and apply it, even though it's just one event, to understand our process in our galaxy. And you're also probably aware there was this fading kilonova from this event. Igor will tell us more about the observations. And my goal here is to try to explain the physics of the kilonova, what produced this fading glow of light, how we immediately understood what we were seeing. But before we can talk about what neutron star mergers do, we need to remind that we don't actually know the properties of neutron stars perfectly well. We don't know what is their equation of state as we go to high densities inside the core. Our traditional models for calculating what the pressure should be from that dense nuclear matter fail for various reasons. And so we, in some sense, have to measure, it's better to measure empirically the properties of neutron stars, such as their radius or mass. And once you've assumed one of these equations of state, and different people have different assumptions about how you get these, I don't have time to go into that. It basically predicts a relationship between the radius and mass, okay, which is usually of this sort of form. So roughly across a fairly wide range of mass, you have roughly a fixed radius, but we're debating exactly what that radius is. So one thing a equation of state predicts is the radius, say, of a 1.4 solar mass neutron star. Keep that in mind. That's one parameter which could describe a neutron star equation of state. And the other is, what is the maximum mass before it collapses to a black hole? What is the maximum allowed for a stable TOV solution? And again, this depends on what the pressure is in the very center of the neutron star. And really the best we can do is put lower limits on this by actually measuring masses of pulsars. And so I think the current record holder is around 2.1 solar masses. So we know the maximum mass of the equation of state can support, which is sort of where these equations of state terminate here. It has to be above 2.1 or so. And we also have information now that suggests the neutron star radius is not, terribly different than, say, 11 kilometers, 12 kilometers. Okay, so what happens when, and by the way, people should, oh, yeah, sorry.
I'm sorry, on the last slide?
Yeah.
Like, which equations of state are sort of diabolical and which ones are
Diabolical?
reasonable? Like, I noticed you're not marking the green one, which would predict a maximum mass above 2.5.
Yeah, so the green one I would say is, I mean, I think it depends on, I don't think it's ruled out, but I mean, for example, some of these, like this blue one here, which is terminating below 2, I would say we can almost eliminate that one now.
But is there a group of equations of states that
are
more
preferred?
favorable, more favored just in the community?
I don't know. I mean, when I talk to people, I think it very strongly depends on your approach. Some people take it from trying to take properties of nuclei and extrapolate them to high densities, and then other people try to do effective quantum chromodynamics expansions, and they come up with some different thing.
Okay.
So I don't get a sense that, I mean, I wrote a paper in 2008 where I made the blasphemous statement that it's possible 2 neutron stars could merge and it wouldn't make a black hole. And I sent it in to referee, and I was told it was impossible because the maximum mass can't be larger than 1.6 solar masses. And because they would create pions and it would soften the equation of state, and you're like crazy. And so I ended up having to change my paper and emphasize more a different model. And then, of course, a year later, De Morris discovered this 2.0 solar mass neutron star. So I don't put a lot of credence in what people say in this community. Okay, I'm re-recorded. But I feel there's a lot of freedom. That's my only feeling. Okay. I'll answer your question. Okay, so
question.
Yes.
Yeah, on the last slide, it seems like as you go through all the different equations of state, most of them fall. Sorry, Keisha. On the previous slide, seems like most of the equations of shape have roughly the same, or like the same shape, but peppered throughout, you have gray ones that don't follow that kind of backwards L curve. Why?
Yeah, I think some of these, I have to remember, I think some of these are where you have deconfined quark matter or something. So it's like strange matter equations of state, and they behave differently than the baryonic ones. So yeah, I'm not the world's expert here, but I think these are like what people would call sort of quark stars or strange stars. And one of the goals is to try to, so a lot of those models you would think now are ruled out because these gray ones sort of terminate here. But of course, the people who work on this say, oh, well, there's a phase transition above some density, so I could have ordinary nucleonic matter down here, and then above some density, I become a quark, deconfined quarks, and then I sort of attach one of these equation states onto a different one. But yeah, that I didn't say that, but I think some of these weird models are sort of non-standard assumptions about that, and that they're not neutron stars, they're quark stars. Yeah. All right. I don't want to talk too much about that, but people do. I mean, people do think about merging quarks, quark stars and strange stars, and the goal of this is to, this is one probe of these properties of equation of state. Let me try to sort of go into how that works. So our 2 neutron stars take a long time to merge, depending on what the initial separation is, which depends on the channels, the formation. Could be mega years, could be giga years. And then sort of what we think is the outcome of the merger, and this is based on numerical relativity simulations for the last 20 years. Sort of depends on 2 things. One is the total mass of the ingoing binary, and the other are these properties of the equation of state. How big is a neutron star? What's its maximum mass? So I'm going to summarize very simply what all this work has shown, and there's a lot of twiddlies and uncertainties here still being worked out. But what people have shown is if the total mass of the binary exceeds a threshold that depends sensitively on the radius of the neutron star, then if you're above about 30 to 60% of the maximum mass, the TOV mass, so the maximum mass of a non-rotating neutron star, then the merger product basically immediately collapses into a black hole, like on a dynamical time, which in this case is like the final orbit, where everything at the end is orbiting around sort of millisecond timescales. So that's sort of known as a prompt collapse. And there's fairly little mass ejection. If you have a very asymmetric binary, you get tidal ejection, but you get fairly little mass ejection when you get a prompt collapse. What we think happens more frequently is that the two stars merge and they produce this rapidly differentially rotating remnant, which we'll call a hypermassive neutron star. So it is temporarily stabilized against collapse. So it can actually exceed by some degree the TOV mass because it's rapidly spinning. It's furthermore differentially rotating. So it's rotating faster on the outer parts than on the inner parts. But then what it's believed is that that differentially rotating object is not going to remain differentially rotating. There are many instabilities, MHD instabilities, that cause basically viscosity that wants to bring the object into solid body rotation, and that those act very quickly. And if you do twiddly estimates of how strong the magnetic field is and what would be the magnetic torque, you find that this differential rotation might be maintained for, say, 100 milliseconds, maybe a second. And then as mass goes in and angular momentum goes out, it's generally found that these objects destabilize and they collapse fairly quickly into black holes. But now, because angular momentum was sort of removed to enable the collapse, you end up with a fairly massive disk of material around the black hole. It wasn't, you could get a disk from the tidal material, but this is sort of a self-produced disk by the object itself. So you get a pretty big torus, but it doesn't remain a neutron star very long. It is also possible, so if the total mass of this initial binary is sufficiently low, actually potentially even smaller than this, but let's just say below 20% above the maximum mass, then even once this differentially rotating neutron star has come into solid body rotation, so now it's rotating as a solid body object, basically a breakup, it still does not want to collapse into a black hole. It's stabilized by its rotation, so it can be a bit more massive than a slowly spinning neutron star. But then we think it will eventually spin down through, magnetic dipole breaking or secular gravitational wave emission or something on a longer time scale, which could be, hours, days, weeks, and then make a black hole. Okay, we think it will still, as long as it's still above the TOV mass, when it spins down, it will collapse to a black hole. And so this object, which is a little bit more stable than the hypermassive, we call the supermassive neutron star, and it could cause mischief in terms of the counterparts I'll talk about.
Sorry.
Yeah.
What's the TOV limit for neutron stars? Because for black holes, that's one thing, but for neutron stars, what is the limit?
I don't know, but it's it's a product of this equation of state. It's where these paths terminate. Okay, so it is the maximum stable mass that you can construct for an equation of state. If you have an equation of state that has is stiffer at high pressure, it can support a more massive neutron.
So that would be dependent on the
equation of state. I'm just saying if you pick an equation of state, then these thresholds, scale with that. And this is all very crude. I would say this transition, we do not understand it very well. I have a paper with Ben Margalit where we argued that this threshold is too high, but okay. Oops. All right. So that's my story, and then I have to show you the simulation of emerging neutron star, which is not mine, and it's quite old now, but it goes quickly, so I like to show it in talks. So you're just seeing the final few in spirals. Again, the orbital period here is sort of milliseconds. Near the end, they'll start tidally distorting each other. You eventually get mass ejection out of the outer Lagrange points of the binary. This is called tidal ejecta. And then you form this differentially rotating neutron star in the center, which through probably numerical viscosity is going to collapse to a black hole pretty quickly. In this case, it's also radiating gravitational waves, which is causing it to lose angular momentum, and then you get a black hole. But because you did go through this sort of temporary state, in part, you get a fairly massive torus of material. There's some matter that has too much angular momentum to be immediately falling into the black hole, so it makes a disk around the black hole.
What's the color coding?
I don't remember. I think it's density, I think, in this case, but I don't remember the scale. I mean, to give you a typical scale, these disks are have densities like 10 to the 11, 10 to the 12 grams per cc. But I know in the probably most of the neutron star are 10 to the 14. So I think it's just a density scale, but I didn't put the scale here. And then this stuff out here is much lower density. So what types of counterparts you get from these mergers we think is a sensitive function of your viewing angle with respect to the axis of the original binary. This idea has been around for 40 years from Eichler and others and Paczynski in the 80s that these accretion of this Doris onto the black hole powers a relativistic jet, and that could be a model for producing gamma ray bursts. And in fact, in 1708-17, we did see a burst of gamma rays after the coalescence delayed by around 2 seconds. So this was this famous chirp with the delayed gamma rays. We're still sort of debating exactly why the gamma rays were delayed in this event. We know that we weren't viewing this event on axis. We were off axis by 10 or 20 degrees, 20-ish degrees. And so we don't think we were seeing direct internal jet emission. We think we were seeing something else. But there's still a question as to whether this delay of 2 seconds is because it actually took 2 seconds to activate the black hole jet that made the gamma ray emission, or whether it took that time for the jet to propagate through this cloud of debris that was created when the stars slammed into each other. And Rem's worked on this. We think this may not even be it may be more like akin to shock breakout emission. I'm not focusing today on gamma ray emission. I just wanted to emphasize that that's sort of an open question people are dealing with. But then you have these different sources of mass ejection that are more isotropic. And as this neutron-rich material decompresses into space, it will power the optical infrared kilonova, which I'll talk about. So the key point is that there's different sources of mass ejection as a function of time approaching and following the coalescence. So this is just schematic. There are actually other sources of mass ejection, but these are the main ones that I think are relevant. The first one is what I call dynamical. So this is the matter that is occurring like right at the end, like the tidal material that's ejected from the Lagrange points. It's coming out on the dynamical timescale very quickly, high velocities. You can also get matter when the stars collide that's sort of being shock heated and sent into the polar direction. This stuff is coming out very fast, but it isn't always that much in quantity. So, if you have an equal mass binary, as I said, I think 1708-17 probably was. It can be as low as a thousandth of a solar mass. But then if you form this stable hypermassive neutron star, it's believed that it will acquire a strong magnetic field because it's rapidly rotating, it's differentially rotating. There are many works that show that the magnetic field can be amplified in this remnant. And so there may be a brief phase which is akin to like a magnetized outflow from this neutron star. This is not proven that we can get these large scale fields, but it's quite plausible. So for as long as the neutron star is surviving, if it has a very strong magnetic field and it's rotating at 1 millisecond, which it is, that wind from the magnetar could produce an outflow of material, which could amount to up to 100th of a solar mass or so, maybe more if it survived longer. And then, as I said, we think in most cases, the object collapses to a black hole, but it's surrounded by an accretion disk, and there will be winds of material from the disk over the following seconds as it consumes this disk. And this can amount, I think, to substantially more material, as I'll talk about in 1 second. And it's believed that the black hole is what powers the GRB jet. It's possible that this magnetar could also power a fast enough jet to get a shock breakout, but that's another question. So what about these black hole outflows? So we did some of the early calculations with Rodrigo Fernandez about this. This was a calculation we did with Dan Siegel right before the merger, where we did MHD simulations of this torus, where we just set it up around the black hole. But anyways, the point is that these disks produce turbulence due to the magnetorotational instability. Not surprising that you get rapid accretion onto the black hole. The material in these disks is very hot with temperatures in excess of an MeV. So these disks cool efficiently through neutrino emission. And you might not be surprised to learn that black holes are fussy eaters. If you put a disk around them only a fraction of it actually is consumed by the black hole. The rest is ejected in a wind. I could go into exactly why this happens. It's partially because these disks are so hot that they're composed of free neutrons and protons. And as you have outflows from the disk or it spreads, those particles recombine, and that formation of helium releases a sizable amount of energy, which helps unbind material. But in the end, we found that around 20–30% of the torus is ejected in a wind with a typical speed of around a tenth the speed of light. This is not the black hole jet. This is wide angle outflows from the wind. I guess I'll show you the actual simulation. And so you see that there's a sort of evaporation of material from the disk. This part of the disk can cool through neutrinos because it's hot, but the lower temperature atmosphere cannot. And so when you get viscous heating or turbulent heating up here, it just goes into driving an outflow of material. And this has been studied by many groups recent, not from this setup, but even starting from the full GR and following the simulation. So these outflows from the accretion disk or from the dynamical ejecta is where we get this R process. So I want to remind you guys, if we talk about electron fraction, it's ratio of protons to total baryons. Okay, so if we blow up a white dwarf, which has roughly equal number of protons and neutrons, carbon, oxygen, etc., the electron fraction is 1/2, and it tends to want to produce nickel 56, as Rem discussed. In these disks, it's much more neutron rich, so many more neutrons than protons. I could go into why that's the case. It's obviously a neutron star, so that's one reason, but the weak interactions also tend to make it neutron rich. So how does this R process work? So we have different phases. There's 4 phases I've listed here. There's the sort of dynamical ejection, so the outflow of material from the disk. These are just all tracers from one of our simulations. Initially, the matter is very hot, so the weak interactions, for example, the capture of electrons on protons and positrons on neutrons, or these neutrino interactions are very rapid. But as the temperature goes down, those interactions freeze out. So that sort of fixes, for some given trajectory, that fixes your electron fraction. And then, as I said, very quickly, your protons get together with some of your neutrons and make alpha particles. This is very rapid because it's so hot. And then your alpha particles basically undergo a triple alpha-like reaction, and then they capture the carbon that's produced, captures more alphas. And so you're able to very quickly go all the way up to these heavy seed nuclei. So this is as far as sort of standard thermonuclear reactions get you. As I said, beyond that, the Coulomb barrier is prohibitive, so you don't get these types of reactions anymore. But you have a huge number of neutrons left over after this because there's only so many alpha particles formed. And so then these seed nuclei that you form at this temperature over the ensuing second or so capture neutrons and move up to these heavy elements, as Rem discussed. So we have this Anna Friebel's little picture here happening in an expanding fluid element from the disk outflow. So here's a nuclear reaction network. This is exactly what Rem showed yesterday. Proton number, neutron number. This is after the material is expanded a bit. So we formed this. This is showing you the concentration, which is the sort of sea of seed nuclei. And then as we let the simulation go, we have a ton of neutrons. So as we let they're sort of down here in this corner. As we let the simulation go, these nuclei will capture neutrons, which move them this way, and then beta decay, which move them this way. And by doing that in succession, we're able to move up to these heavier elements. And so on the right here, you're seeing a running, the temperature and density dropping as a function of time as this fluid element expands. And along the top, you're seeing a running accounting of the synthesized abundances. And so, oops, let's see if I can get it to run. Okay, so we're capturing neutrons, we're decompressing, and then around 1 second or so right here, we run out of neutrons, and then everything slowly decays back to the stable valley over minutes, hours, weeks, etc. Okay. So at the end, we start off with a fairly modest distribution of seed nuclei, and at the end, we end up with a very broad distribution of nuclei due to all of these captures. And so you end up with a sort of a final abundance pattern that looks something like this. The solar system abundances are shown with the diamonds here, but you get these. You characteristically get these peaks, the second and third R process peaks, and that occurs because there are closed nuclear shells at which this flow tends to build up. So where the neutron capture timescales become very slow, and so as you go up, there are sort of localized regions where you have particularly stable nuclei, and the flow kind of builds up around those. And then when they decay back, you end up preserving those abundance peaks in the final pattern. But this is sort of details. As Rem discussed, interesting thing for Kilonovae is that you've created all of these radioactive elements, which as they decay back to stable elements, release heat in the form of the radioactive decay. So this is the radioactive power in ergs per gram per second versus time. As we talked about, nickel and cobalt have this simple, right? If you have a single isotope, it just has a constant radioactive heating until you reach the half-life, and then it decays. So nickel decays into cobalt. But here we have, hundreds of nuclei, right, as Rem discussed. And, at any given time, your heating is dominated by the nuclei, which have a half-life, which is of order, that time. And so ones with short half-lives decay into ones with longer half-lives. And when you add them up in aggregate, you get this sort of power law type heating, mostly due to beta decays and alpha, mostly due to beta decays, but there's also fission and alpha decays that contribute to the total heating. And so we were the first to calculate this in 2010. There had been some earlier work by Leon Paczynski, which estimated this as T to the -1, but they didn't nail down the normalization. So it could have been, Kilonova could have been superluminous supernova, or they could have been these dim. So the real thing that we did here was to actually calculate this. So when we're talking about kilonova, as we'll talk about, remember that we have this peak diffusion time. I'll come to this in a second, but what we really care about is what is the heating timescale at the time the radiation is actually able to get out of the ejecta, which is days to weeks. And so on this timescale, you can sort of roughly approximate the heating for a given amount of ejecta mass with the following formula. And I'll come to this in a second. This is the thermalization fraction. So this is just the total heating. So not accounting for how much goes into gamma rays or neutrinos or beta decay electrons. So we have to correct this for what we think is the fraction of the heating that is actually going into the plasma. But this is a typical number you should keep in mind. At one day, if I have 10 to the -2 solar masses of our process material, I get a heating around 10 to the 41. So this is a very complicated topic of thermalization, and I'm not going to say much about it. I just wanted to throw up a few slides. If you're interested, you can read Jenny Barnes's paper. There's some stuff also by Kenta and also by Eli Waxman's group. But the point I want to raise is, depending on what you assume about the equation, the nuclear mass model, which is what controls the masses of nuclei when you get off of the stable valley, you could do different quantities of heating through beta decays, alpha decays, and fission for very heavy nuclei. It turns out that for the alpha decays and fission only really matter for very, very neutron-rich nuclei. So there's very low electron fraction, around 0.1 or so. So most of the heating does come out in beta decays, but there are these additional contributions. And then once you know what is the heating, you have to determine how much of that heating is actually thermalized, how much of that energy release is actually thermalized. And that depends on whether you're emitting gamma rays that have to Compton scatter to get out of the ejecta, or energetic electrons, or whether you're emitting alpha particles or fission fragments. And it's a bit complicated, but the total thermalization history efficiency, which is sort of the sum of all these things weighted by how much they contribute to the heating, is typically of order unity at the first few days, like a half or so, when the gamma rays are trapped and everything is thermalizing nicely. But then it drops with time as the ejecta becomes more dilute. And you have to include this in your modeling on top of, so it makes this radioactive decay effectively steeper than this. So going back to lecture 1, when we did over these analytic estimates, if I have an expanding ball of gas with some velocity and ejecta mass and opacity, I just want to go through what those would apply here to kilonova. Of course, kilonova are not spherical, but neglecting that, we recall that the light curve, the radiation is able to get out faster than the ejecta is expanding on this sort of peak time scale. And so if you put in a typical ejecta mass for a merger, 100th of a solar mass, 0.1 C, and an opacity, I'll come to that, what that is in a second, of 1 centimeter squared per gram, you see that the estimated peak time for a kilonova would be around 1 day or so. And the peak luminosity, as you remember from Arnett's laws, you just take the radioactive heating rate and you evaluate it at this peak time. So if you do that in the context of that model, you find that the peak luminosity is in about 10 to the 41 for these values of the mass and opacity. And you can even go so far as then to estimate a peak effective temperature. If you say, okay, the photosphere is not terribly different than the characteristic radius of the ejecta, you can even estimate the photosphere temperature. And the thing I want to emphasize here, 3 facts, is one is, as we'll find, depending on exactly what our process elements are produced, we can get very different opacities here. So if I have higher opacity material, I will have a longer transient, it will peak at a lower luminosity, and it will be redder. Okay, makes sense. If the opacity is higher, the ejecta has to expand further for the radiation to get out. By that time, the radioactive power has gone down, and the temperature will be lower as well, because it's larger and luminosity is lower. So in 2010, we did make these first predictions based on the first time anyone calculated the radioactive heating of the events, and so this was literally like our figure 1 of 10 to the minus 2 solar masses expanding at a 10th speed of light. And you could kind of see this sort of peak at a few 10 to the 40. We were assuming 100% thermalization here. We did talk about thermalization, but we didn't worry about it too much because we thought people would be lucky to detect this phase. And so what we said is, okay, well, this is around 1,000 times brighter than classical nova in our galaxy. You'll learn about on Friday. So we called it a kilonova. And then you can kind of see after the peak, as expected, the light curve will follow roughly the radioactive decay. These bumps and wiggles are due to the fact that in these early models, we assumed iron opacity. And so as iron ionization changes, you get kind of weird bumps, but they're not going to be there in the actual kilonova. And so it was very heartening when this event was discovered that I could literally take our first model and you could just put the bolometric light curves from 1797 right on top of it. And it actually worked remarkably well. Now, this is not to say this was in any way fine-tuned, but I mean, to me, it was clear what we were seeing, at least at that level, from this event. But one important aspect of 17017 is this very strong blue to red transition in the color, okay, which was not predicted in these early models. Oops. This is this compilation from Ashley Biller showing the sort of bolometric data from this event, where in the ultraviolet, the light curves decayed very quickly, and in infrared they lasted longer. And so this kind of goes back to sort of very fast and blue emission to very slower and red emission. And as we talked about, what sets the colors and timescales of kilonova is intimately connected to the opacity. And the point I'm going to make in a second is that we believe that there may be reasons that there are distinct components of ejecta from the kilonova which will have different opacities. And so you could explain this blue to red evolution if you said that there were really a gradient of opacities, or there are different opacity components. And so if I want to explain the infrared part, I need something with a high opacity that's going to produce a longer peak time scale and a lower effective temperature. And if I want to explain this early blue component, I want something with a lower opacity. And as I'll talk about in a second, it turns out that depending on which R process elements you synthesize, whether you just synthesize the lighter ones, which have these D shell valence electrons, or whether you also synthesize these lanthanide and actinides which have F shell valence electrons, we think they have very different opacities, because what's setting the line opacity, what's setting opacity in these is line emission. So I'll talk a little bit. I guess I'm going to show you the details in a second, but this was predicted by Dan Kaysen and Jenny Barnes, that if you just have these lighter R process elements, you should get a bluer emission with a lower opacity, which peaks on around a day. But if you have lanthanides in the ejecta, then it will be significantly redder and peak around a week. And this is some of the early models of this. I'm going to talk about what physics sets this right now. Oops, sorry, it keeps. Okay, so the key point, and I'm not going to belabor this too much, is that the dominant source of opacity are bound transitions, atomic transitions. And basically, the more those transitions you have, the more lines you have, the more opacity you have. And so if you look at the number of transitions that elements have as a function of the valence structure of the electrons, there are many, many more transitions for atoms which have F-shell valence structure, meaning the lanthanides and actinides, than there are even for things like iron, which have D-shell valence electrons. And so if you translate this number of lines, it's sort of a combinatorial way. If there's many more ways to rearrange, the electrons in the shell, there's going to be many more transitions. And so if you look at the and this is based on an atomic structure calculation by Tanaka. What you see is if you then translate the number of lines into its mean opacity, Sobolev opacity, if you have the lanthanides, basically they have much higher opacity. In these units we've been using centimeters per gram, it can easily be tens, if not hundreds. Whereas for the sort of iron group elements, it's closer to, as we discussed, 0.1 or 1. Okay, so you could get easily a factor of 100 difference in opacity depending on whether you have lanthanides or actinides in the ejecta. And what determines whether you have lanthanides or actinides in the ejecta is whether you have enough neutrons during the neutron capture process to actually get up to these heavier lanthanide elements. And so there's this prediction that if you have very low Y ejecta, which has lots of neutrons, I can easily produce these lanthanide actinide elements. I will have a very high opacity of my ejecta, very red emission. If I just have a little bit of neutrons, if I have an electron fraction which is closer to a half, enough to produce these lighter R process elements, but not the heavy ones, then they will have a lower opacity. Okay. And so this gave rise to this notion of separate red and blue kilonova, whether they have high opacity or not, whether they produce lanthanides or not. Again, there's something intermediate called a purple kilonova, but don't get me started. Yeah.
Just a quick question.
Yes.
So I was wondering about this sketch that you showed earlier from the analytical derivation, how well it's fit by, that one.
Oops, sorry.
How it's well fit by the data. And then later you talked about the blue and red component. I don't quite understand if in this picture you're already considering multiple components or just a bolometric.
Yeah. No, it's a good point. I would say from the bolometric light curve, we don't need the red component. Like you could explain the entire bolometric light curve with a modest opacity. I would say the data, it's really when you're trying to also explain the colors that drives you to consider this high opacity. And there's also degeneracy, exactly what the velocity structure of the ejecta you assume. So in some ways it is, we assume some, I mean, this was the fact that, we produced this was probably pretty lucky in terms of what exactly we had assumed, because we took in this calculation essentially iron-like opacities. So I would say if you just look bolometrically, you don't need these heavier opacities, but you wouldn't get the right, we didn't predict the right color evolution, I guess is what I would say. So that's where you need the lanthanides. Okay, I need to hurry up a little bit. Okay, I will say though that like, some people say, oh, you're over-interpreting things. I will say the reason that I over-interpret things is because we were thinking about these things before 170817. And so we're biased in some ways. We were, I wrote this paper with Rodrigo where we said, okay, there's different sources of ejecta. There's these disk outflows we think are neutron rich. There's a possibility that there more proton-rich or less neutron-rich material from the collisions or this magnetar wind. And so we had even discussed that there could be two components in the ejecta, blue and red separate components. And so if you model 17817 this way, anyways, you find that in these sort of two component models, you find that you need a little bit less mass in the blue component. It has to be expanding faster, and you need more mass in this red component. It has to be expanding slower. There have been many works since then. This is all sort of two spherical cowl models. We can debate how much those works have changed the qualitative picture. I think there are a lot of uncertainties, but I'm convinced there's some neutron poor material and some neutron rich material present in these ejecta. And so, okay, but I'll come back in a little bit to how this might change for future mergers. But one of the questions you always get asked is, okay, are mergers the main source of the solar system, our process? What did we learn from 17817? Well, what you can do is you could say, okay, how much our process production had to occur in the Milky Way prior to the formation of the sun. So you could count up all the R process elements, you divide by the age of the galaxy, and you figure out that to produce these elements, we need a few 10⁻⁶ solar masses of production per year. Then you can say, okay, how frequently do mergers occur in Milky Way type galaxies? And of course, LIGO has a huge range in its merger rate. You translate that to a Milky Way rate. You find that each merger to produce this rate would need to produce between a few thousandth and a few tenths of a solar mass per event, okay? So this one event, which we think produced a few hundredths of a solar mass, is sort of in the middle range. So we could say, okay, it's possible that mergers produced all the R process elements in the galaxy, but there's huge uncertainty still in the rates, and people will debate the uncertainty in what this event produced. So I would say we don't know. I would say it's very unlikely mergers don't produce at least 10%, but we could produce 99%. And I think, until we have more events, that's going to be hard to parse. So one interesting is what actually produced these components in the ejecta. I already told you about these different tidal outflows, disk outflows. Here's my view, which may differ for other people. If you take all of the simulations that predicted the dynamical ejecta, because in the early GR simulations, they couldn't follow this accretion disk or these magnetar winds. They would stop the simulation right after they merged. And they would predict how much mass was ejected and with what speed it was ejected at that point. This is what I call dynamical ejecta. And you just plot it, sort of see clouds like this. They're varying the equation of state, varying the mass ratios of the binaries, blah, blah, blah. And then we think to explain the Kilonovae 7807, you had the blue part you needed to be kind of here, and the red part you needed to be kind of here. So what you'll see is that none of these simulations predicted enough material ejected, or with the low velocity that we think we needed to explain the red component of 17817. So my view is that most of the ejecta, maybe some of the blue component, but most of the ejecta do not come from dynamical ejecta. It actually came later from the accretion disk outflows, which we had predicted should have speeds closer to around 1/10 the speed of light. And if you're ejecting 30% of the disk, it's easy to get up to a few hundredths of a solar mass if you have a fairly massive disk after the merger, which is what simulations predict. It could also be the case, as I said, that this magnetar, there's Sanjana Curtis is doing a lot of nice work on this scenario. We do think that the Kilonovae colors, this quantity of lanthanide and actinide ejecta is probably sensitive to the lifetime of the neutron star before the black hole is formed. This is something we pointed out in 2014 with Rodrigo. We did a series of these simulations where we evolved the evolution of the post-merger torus, but we varied the lifetime of the central neutron star artificially. So we had it collapse to a black hole, 10 milliseconds, 30 milliseconds, 100 milliseconds, 300 milliseconds, or never. And then we just calculated how much of the ejecta had different electron fractions. And then you could break it down into whether they would produce more bluish ejecta or more reddish ejecta. And what we found was that the longer the remnant survived, the more neutrinos from the neutron star irradiated the neutrons and turned them back into protons. And so the higher the electron fraction was. And we found that, and also you tended to increase the total amount of mass from the disk winds, obviously, the longer it survives. And so we found that so you predict more and bluer kilonova with the lifetime of the remnant. We followed this up with Dan Kaysen a year later, and we sort of predicted how the blue component would get brighter for longer lived remnants. And there's been a lot of, so my view is, however, if you look at the longest remnants, if you looked at the ones that survive forever, they basically produce no red kilonova ejecta. So it's sort of my view based on this that the fact that we did see some lanthanide rich ejecta with low velocities is supporting that there was a black hole formation in 17817. And seeing very recent work by Sanjana's group, this appeared on the archive a few nights ago, I think also comes to this conclusion with more updated end-to-end simulations. So going back to this pathways thing, we can ask the question, okay, which pathway did 170817 follow? And I didn't say this earlier, but the name of the game is LIGO and Virgo tell us what's going in, and then you observers try to tell us what's coming out. And then we try to meet in the middle and constrain these pathways, whether this is even the right picture, whether we can learn something about the equation of state. For 17087, we were able to measure the binary mass. And so that allows us, if we can rule out any of these outcomes, that allows us to constrain the equation of state. So I would say just the fact that we got so much kilonova ejecta, it's very unlikely that we had a prompt collapse. And so it turns out, well, I'll tell you in a second, but we can rule out a prompt collapse, which ends up constraining, it turns out, the radius of the neutron star. I also think we can rule out a very long-lived supermassive neutron star. One piece of evidence is that the kilonova is too red. The other piece of evidence is that the kinetic energy released by the kilonova and the jet were, I think, too low if we really had a rapidly spinning neutron star. I'll get to that in a second. So by elimination, and also by the prior that this was what most numerical relativity simulations predicted for this mass, most equations of state, we think 17087 probably went through a hypermassive neutron star phase and did make a black hole. So you can again ask, what implications does that have for the equation of state? It turns out that this constraint, this threshold depends on the compactness of the neutron star. So if you infer that 17087 did not make a black hole, you could actually put a lower limit on the radius of the neutron star. Likewise, if you assume it didn't make a supermassive neutron star, you can put an upper limit on the maximum mass of a neutron star. So if you sort of combine the different, I should make a formal version of this, but if you sort of combine the different constraints we have for 17017 based on the tidal deformability, which constrains the radius from above, the no collapse condition from below, and the fact that it didn't make a long-lived magnetar, we argue, the number of equations of state that actually can satisfy all these things is being reduced. Now there are a lot of debate at the boundaries. Okay, what is the fuzziness of these boundaries? But I think this is the general way forward. This is multi-messenger astrophysics, is like combining what we see electromagnetically and what we observe gravitationally and learning something potentially. Okay, we'll hear more from Igor. I think, we hope to see more of these events to really test this. He'll talk about the future of that. I just want to go through quickly, since I'm running out of time, and sort of argue, well, what would be the prediction? If this is right, you should make a prediction for the next event, okay? If something is more massive or less massive, it will do something different than 1700817. So what are the predictions? Okay, so the prediction is if I have a more massive binary that does undergo a prompt collapse, it will eject less material. There will be no central neutron star, so no source of neutrinos to turn neutrons back into protons. So the electron fraction will be lower, and I'll have less material. So it should be dimmer and a redder kilonova. Easy prediction. Of course, we did have such an event in 2019, 190425, which, unlike the first binary black hole, was right smack in the middle of the total mass of the galactic neutron stars. This event was substantially more massive. We think it was a neutron star was involved, 2 neutron stars. But so if this was 2 neutron stars, the prediction is it should have produced a very hard to detect red dim kilonova. And unfortunately, we didn't have very good sky localization. There was no counterpart found. Igor may talk about this. So we couldn't really test it. Like, we couldn't rule out absolutely 17817 like Kilonovae is my understanding, but that would, hopefully we'll get another event like that. What if we see a substantially less massive binary neutron star that could go through this supermassive phase? So as I said, it's very likely that this neutron star is highly magnetized. It has an enormous differential rotation, rapidly spinning. It probably has a very strong internal field and potentially external field. So the prediction is that we should see a brighter, faster, and bluer kilonova because of various reasons. The stronger lifetime, you have more neutrinos. You start to get energy also from the magnetar. Ben Margalit made a nice image of this, sort of the different outcomes of energy release if you change the mass of the ingoing neutron stars. And so if you promptly collapse, very little mass is ejected, so you get just a tiny kinetic energy of your kilonova. If you form this hypermassive neutron star, you get some disk winds, you get a little bit of dynamical ejecta, a bit more, so of order 17817, 10 to the 51 ergs. But if you form a stable neutron star, it has to lose spin energy to collapse. So there is a necessary removal of energy to make a black hole. These events are great. You can hide the energy in the spin of the black hole and it never comes out. But if you actually have to spin down to collapse, that energy has to go somewhere, and it has to either go into the kilonova or the GRB jet or something we should see. And these become quite enormous energies. These remnants can have 10 to the 53 ergs of rotational energy. So these should be very conspicuous, I think, observationally. Stated another way, if you did have a magnetar in the center with a magnetic field of order 10 to the 14, 10 to the 15 Gauss, it would have a spin down power which is far exceeding the radioactive power from our process. And so we could get an analog to superluminous supernova powered by magnetars, but where the magnetar is now embedded in this tiny ejecta mass of the kilonova. I didn't cite it here, but we did some work with Tony Pirro, Bing Zhang's group's done work on this. Anyways, I think these would be very conspicuous. Now, there are some people will say, oh, there was a merger here, but like 99% of its energy went into gravitational waves and was like hidden from us. I find this very unlikely. I think if we do get these stable low mass neutron stars, and this is why it's so important for LIGO to tell us what the chirp mass is, because if it's very low, this is something we should prioritize in the future. Of course, we don't have enough mergers now that we have to worry about that, but
Sorry?
yeah.
Do we know what's the mechanism of the collapse? Is it accretion driven or is it the spin down driven collapse?
For this phase, the hypermassive neutron star, you might think of it as accretion driven because it is sort of matter that's going into the core from the redistribution of angular momentum. But down here, I'm talking about spin down induced. The disk is gone. I have a magnetar and it's spinning down over, hours or days or something. So there's no disk left. So it's actually, the collapse in this case is driven by the either magnetic or gravitational wave spin down.
So this is for the long lived.
Yeah, this is for the long-lived or indefinitely stable. I didn't talk about this, but this is a channel. If you somehow had a merger that had, if the TOV mass was so high that I could actually merge two neutron stars, then it would be below the TOV mass. It would never make a black hole.
Sure. And for the not long-lived neutron stars, for the middle channel, that you showed in the previous slides.
Yeah. These ones, the hypermassive ones, you might think of their collapse as accretion driven, but it's more like a redistribution of angular momentum in this star-like thing. But yeah, accretion from the disk could contribute to the collapse in this case. But the disk doesn't survive. The disk survives for a few seconds. That's the sort of accretion time of the disk. So if you're talking hours or days afterwards, there's no disk left. There's just this remnant.
So how would it be accretion driven?
Not at late times in this phase, the hypermassive case.
Yeah, the hypermassive
it can be accretion. When you merge, you form a differentially rotating neutron star with the disk.
Yeah.
So some of that collapse is due to the redistribution of internal angular momentum, and some is due to the accretion by the disk. And they could both contribute to building up the mass to the collapse point. But yeah, that answer your question? Okay. All right. I'm at 10:06. I'm actually doing okay. All right. Oops. So with Ben, we back in the days of 2019, where we thought there would be lots of mergers, and by now we would be drowning in LIGO mergers. We sort of put together this aspirational vision for sort of trying to tighten these constraints, that there should be some correlation between the mass, the chirp mass that LIGO measures, and the electromagnetic signature. And if our theories, again based on decades of numerical relativity and other semi-analytic work, are correct, we should really start to see delineated boundaries in terms of the electromagnetic signatures, whether they have blue or red kilonova, whether we see GRBs, which probably relate to whether there's a disk around the black hole. I'm not going to go into this in any detail. The idea was that their boundaries between these in chirp mass space are telling us something about the equation of state. And so if I imagine some day in the future where we have hundreds of events and we can say, oh, that was a supermassive neutron star, that was a prompt collapse, that was a hypermassive neutron star, we would be able to see how well delineated these boundaries are. And as I said, they should be, because of this energetic argument, I think they should be fairly conspicuously distinguishable from each other.
So Brian,
Yeah.
so if we do have like this broad diversity, EM counterparts and chirp masses, and that would imply that there's like different equations of state, right? It's not just one EOS.
I know it would, the diversity could fully, this assumes there's just one equation of state, oops. But it's just saying there's a diversity of different binary masses, right?
Okay.
I just have some that are low mass neutron star binary, some that are high mass. We're already seeing with 19045 and 72.7, there is a diversity of chirp masses. So yeah, you would also have to have, nature would have to be kind enough to give you mergers with a range of masses. Okay. And I didn't put slides on this, but the other way we discover kilonova is after GRBs. So as you wait for the GRB afterglow to fade, you see these kilonova bumps. And Jillian Rastinajad has been doing really nice work compiling uniform sets of these GRB kilonova. And we are seeing diversity in the ejecta masses at the level of factors of 10. But it's hard because you don't have the gravitational waves. We can't actually see what was the binary mass for those. So you can look at correlations between GRB and kilonova properties. And I didn't include that here, but that's the other way forward to try to look for diversity. I should say, these 10 to the 53 erg bombs, they should produce very, very bright radio emission. And so we've been following up short GRBs late times with Wenfei Fong and Genevieve Schroeder, and we don't see any evidence for these 10 to the 52 or 53 erg bombs after short GRBs. So it is possible that making a long-lived neutron star, if it ever happens, it's possible that that precludes making a GRB, or it's also possible that these channels are just extremely rare. The maximum mass of a neutron star could be 2.05 solar masses, and almost no mergers would be low enough mass to survive this. And then we would have everything would be up here. That's possible too. So I always finish with this. This was an image we made in a review before the merger of sort of the different phases and what were some of the predictions as a function of time. So you have the gravitational waves, you have the coalescence. Things I did not talk about today is the possibility that the magnetospheres of the neutron stars interacting could produce some kind of radio burst prior to the coalescence. Then you coalesce, you form an accretion disk around the black hole, which takes typically a few seconds to accrete, which can give you a short and maybe even a long GRB. Then you have the ejection of material, which makes these R process elements over the course of a few seconds, as we discussed, but they're radioactive for much longer times. If there's a long-lived remnant, you could also be pumping energy from the spin down of that remnant. And then you see different types of kilonova, mainly determined by how fast they're expanding. The fastest layers, the lowest mass layers, as we've learned, produce the earliest emission. As time goes on, you see deeper into the ejecta. So insofar as if we do have a situation where low opacity material is ahead of high opacity material, then we should see this blue kilonova prior to the red one, which we may have seen in 17817. And then eventually anything that's left goes running into the ISM, and we get a flare from that. So in terms of what we saw in 17817, we did not see an FRB, though nobody was probably looking. We didn't see any. There's other evidence people have said in the X-rays, if you have a long-lived magnetar, you might get some kind of plateau phase to the X-rays. This is rather contentious, but we definitely didn't see any like X-ray plateaus, although again, I'm not sure if we were looking at really soft bands at this early time. There was a prediction that we made that the very fastest ejecta layers expand so fast that the R process doesn't have time to occur. The neutrons do not have time to be captured in the nuclei before that neutron capture process freezes. And so you end up with the outermost 10 to the -5 solar masses of ejecta could be free neutrons. And then all of the calculations Rem did apply exactly to the radioactive heating. And it so turns out that the neutron half-life of 10 minutes is roughly commensurate with when those ejecta are becoming transparent. And so they can produce an early bump in the light curve that's brighter than what you would get from the R process heating alone. And I called this a neutron precursor. There are other ways that the GRB jet might produce early UV emission. So there's a lot of interest with ultrasat, for example, in trying to get on to these very early to either look for jet signatures or this neutron precursor. But we did not see it in 17817. The earliest observations were at 11 hours. Okay. How much time? Maybe 10 minutes or?
Yeah.
Okay. So you may come to believe then that mergers make all of the R process in the universe. And it's very funny to me because when I was coming up in this field in the 2000s, I was under the strong impression that studying mergers was like a crackpot thing. That supernova were clearly the site, and everyone was kind of tweaking the supernova models to make them work, and they never worked. And so I started thinking about other sites of the R process. In fact, a lot of my work was thinking about newly formed magnetars in supernova as sources. So tweaking the supernova models. And there was some good reason. People had this notion that mergers were old events. It would take forever for the two neutron stars to come together. And there was a lot of evidence that what was polluting the universe in our process could happen fairly early in its chemical evolution history. And these really haven't gone away. I think there are evidences that some R process sorts are prompt. And it could be mergers, could be prompt. But it could also be that there are multiple sources. So two pieces of evidence is that we have these ultra-faint dwarf galaxies like Reticulum 2. Most ultra-faint dwarf galaxies have basically no R process elements in them, but a few are enormously polluted in R process elements. And this is a bit surprising because these are very old galaxies, so we would need a very prompt enrichment to enrich these stars before they finish their star formation. And because they have such low escape speeds, we would need to be able to keep the binary neutron stars in the galaxy so that they would merge in the globular cluster. And Paz Beniamini, Steve Perron have argued it is possible to do this for mergers, but whether all these conditions can be met, it would be very easy to just make this some kind of supernova or thing tied to supernova or a young stellar population as well. If you look at the ratio of europium to iron in the galaxy for different stars, so this is metallicity, this is the europium to iron ratio, these are stars around the sun. You also see some evidence that europium was formed early. Europium is an R process element mainly, that it was formed prior to iron, and iron, of course, comes from type 1a supernova, as we've learned. So what you see is that the ratio of europium to iron versus metallicity drops, okay? And of course, iron is being produced at late times, but this is telling us that europium was produced before the iron, so that this ratio will drop as iron turns on. And if mergers had the same delay time distribution as type 1a supernova, you would expect basically a flat line here, but it's declining. So this suggests that there is some prompt R process channel. I'm not saying it's not mergers, but we should keep our eyes open for other sites of the R process. And there are a lot of things people have talked about. The traditional models involve winds from the newly formed neutron stars in ordinary supernova. As I said, this was popular in the 90s when it seemed briefly to work. It no longer works. People have worked on variations of this scenario where we make the central neutron star highly magnetized. This was my PhD thesis. It does seem to work. There's some very nice work by Tejas Prasanna showing that magnetized protoneutron star winds can produce a bit of our process elements. But we don't know, whether these magnetars have these strong fields so early in their evolution, right after they form. We don't know if it's enough. We don't know how rapidly spinning these magnetars are. There's mergers we've already heard about. There's thoughts that maybe the accretion disks around black holes in long GRBs, collapsars, could make our process elements. I could talk about that, but I'm not going to. I think the basic point is if you feed a black hole at a high rate, the material around it will become neutron rich. And the question is how much gets out of the collapsar. Some nice work by Donat Isa has shown recently that it may be possible to get some R process elements out, but that's an open question still. We can look at late time spectra of collapsar GRBs to try to search for evidence of these R process. But I want to tell you in the last 5 minutes is that with Ani, I'll tell him this is to his credit. We think we have direct evidence that there is another R process site in the universe, and this is magnetar giant flares. So this has sort of come out of left field. If you had been following this, I don't think there was much discussion in the literature until very recently that these giant flares could produce R process elements. But just so you're aware, magnetars are these highly magnetized neutron stars in our galaxy that are powered. They have X-ray non-thermal emission, which is powered by the decay of their very strong magnetic fields. They are actually quite common. They might constitute up to, I don't think 60% is likely, but they probably constitute, 30% of neutron star bursts. They have these enormous giant flares, which happen in our galaxy every few decades or so. There have been 3 in recorded history where they release 10 to the 44, 46 ergs of energy. And these giant flares produce an enormous gamma ray burst, and then it's followed by a tail of X-ray emission, which is a giant fireball of plasma, which is trapped on the neutron star. And as it rotates, you see this modulated X-ray emission. So the analogy is some kind of coronal mass ejection from the sun. We don't know what powers these giant flares. And we can even see them sometimes outside of our galaxy as short gamma ray bursts. So a small fraction of short GRBs are not merging neutron stars, they're the giant flares. And the most recent one of these that was detected outside of our galaxy happened just a few years ago in M82. Okay, so we don't know exactly how these giant flares occur, but we do have evidence, as I'll come to in a second, that they do eject neutron star crustal material into space. So to study this or parameterize it, we set up a simple model with Jakob Sahula, where we basically took a neutron star and we said, okay, I don't know how a giant flare releases energy, but let's assume that it does. And it produces a high pressure region above the star. And we just let that go. So the idea is that the reconnection produces electron-positron pairs and photons and creates this kind of fireball above the surface. And it's, at least along some directions, unconfined from the magnetic field. So as this high pressure shell expands, it will produce a very relativistic outflow. But there will be a brief period of time where that high pressure shell drives a shock into the surface of the star. And once the flare is gone, that overpressurized crust now can re-expand, and so some of the crustal material can be ejected. And so Jakob did simulations where he tried to estimate exactly how much mass and with what speed it was ejected given a particular amount of pressure in this shell.
Sorry,
Yes.
how do you model your neutron star? As in, how do you make it different from, say, a black hole? How do you make it not, your model not agnostic to the central engine?
Here the difference is a neutron star has, there's actually matter there, so there's no horizon. We're not doing anything sophisticated with the space-time here. We're just trying to get an estimate of the mass ejection. So we just even assume Newtonian gravity here. But you're right. We should be doing GR. It's a neutron star. But the difference is there's no black hole here because this is just an ordinary neutron star. And the black hole has no crust, right? So there would be no baryons. Black holes have no baryons.
So, sorry, Siri was talking over you. So you said that you have some boundary conditions. What do you have? So surface or?
Yeah, there's a surface, inner surface, and then we model the atmosphere of the star above it as some gamma law polytrope, and then we initialize with some high pressure shell, and we assume a gamma 4/3 law for the pressure. All this is very radiation dominated.
So ideal gas.
Ideal gas for this calculation, yeah. So it's very simple setup. But this compression, you get a very thin, region. It's hard to resolve. You need a lot of resolution in the atmosphere of the neutron star. It's not an easy problem.
No, it's not.
But the point is, we don't actually think this is the physical mechanism. We don't know what is mechanism. We just want some way. Well, maybe I didn't include slides. Did I not include slides? I didn't. What I will say, okay, I'm running out of time. What I will say is that we do have evidence that these giant flares do eject material. There was a radio afterglow to the 2004 giant flare, which was modeled as 10 to the minus 7 solar masses ejected with a speed of half the speed of light, and that it was loaded in baryons. And so we were trying to reproduce an observation. And I need to finish quickly, but I will simply say that this decompressing shock-heated neutron star crust material is a good place to go looking for the R process. It's not particularly low electron fraction material, but there's a mechanism where if you have hot enough material, your formation of seed nuclei can freeze out, and you end up being able to produce heavy R process elements because you basically trap some of your protons into alpha particles. And so the seeds that are left are able to take more neutrons on. I don't want to go into this in detail, but Annie modeled this with Skynet, the trajectories from Jakob's simulations, and was able to show that we can get an R process. So we were interested in trying to predict the possible miniature kilonova that we would expect from these giant flares. And see if we could detect them extragalactic with ultrasat. I'll come back to that in a second. So this was his calculation of the light curve, doing the kind of one zone things or multi-zone things you guys did yesterday. He calculated the light curve, accounting for the R process decay. But now we're talking about much less ejected mass, a millionth of a solar mass, rather than a kilonova, which is a hundredth of a solar mass. So the light curve kind of peaks on timescales of a few minutes rather than a few days at luminosities of order 10 to the 39, 10 to the 40 ergs per second. But even though this is not very bright and it's evolving very quickly, we think these could potentially be detectable by ultrasat if it's able to slew quickly to a giant flare detected as a short gamma ray burst in the nearby universe. So these miniature kilonova ultrasat may be able to slew in 15 minutes. UVOT could in principle do this, but the issue is that a lot of the gamma ray error regions are large. So the question is how much it could have to tile. We could talk about that. The final thing I want to say, though, is that in doing this, we then realized that there's an even brighter signal. So giant flares happen in our galaxy. The problem is that they're in the plane. And so this kilonova-like emission would be obscured by dust. The giant flare that happened in 2004 was behind 30 magnitudes of dust. But gamma rays don't care about dust. And as we learned, when you get our process, you produce these unstable nuclei, which decay back to stable nuclei by emitting gamma rays. And those gamma rays can come to us once the ejecta becomes optically thin to gamma rays. And that takes typically around 10 minutes for these ejecta properties. So we're predicting that there should be an extra component of gamma ray emission after the giant flare and the X-ray tail. We should see an extra component of gamma rays. And what we found going back to the data is that there actually was such a component in this 180620 flare. There was a distinct component that rose around 1,000 seconds and then decayed there afterwards. It was mostly ignored by theorists, and the observers had no idea what it was, and it was sort of forgotten about in the history. This sort of MEV afterglow that was seen, but in retrospect, the decay was actually following roughly what we expect from the R process. And so Ani did a more detailed calculation of what would be the actual gamma ray emission from this radioactive decay by figuring out the Skynet output, all the decaying nuclei, what kind of gamma rays they would emit. Spare you the details. He was able to make a prediction for what the gamma ray light curve would be, and the fluence, the integral of that as measured at Earth, and for a model where we ejected a millionth of a solar mass at a few tenths the speed of light, was able to get a nice match to both the peak time and the overall normalization. And furthermore, when he predicted the gamma ray spectrum, and we have to account for the diffusion of the gamma rays, the Monte Carlo radiation transport. This is work by Andrew Boom. We actually see a pretty good fit to the RESI spectrum that was observed of this extra MEV component. So both the fluence, the light curve peak spectrum all match this giant flare producing a millionth of a solar mass of material. And so the final slide is basically to say you can take any site for the R process. And as I said, what you want is to produce the galactic R process. So you need the product of the yield per event times the rate to be above some value over the history of the galaxy. So you could put different sources of R process into this. I think Kento Hotakazaka made the first version of this. But we're making a version where, okay, so neutron star mergers are very high. They produce a lot of R process, but they're very rare. So they could potentially produce most of the galactic R process. But now we're adding a second confirmed R process source, which is galactic magnetar flares, which produce much less per event, but are much more common than mergers. And we estimate that they could produce between 1 and 10% of the galactic R process. So there's at least two sources we think of R process in the galaxy: mergers and magnetar flares, and there may be other things. So go out there and find them, please. And I'll finish there. Thank you.
All right, so you mentioned the possible different outcomes of the neutron star mergers.
Yeah.
And it mostly depends, I guess, on the mass of the two neutron stars. Is there some interesting degeneracy with their individual spins prior to the merger? So I could imagine that there's more angular momentum or less angular momentum, and the merger product that could influence what would be the outcome.
Yeah, there haven't been that many numerical relativity. Most people assume the spins are not that important because you can't spin, like if you could define the maximum rotation period of a neutron star and put it into a dimensionless spin, like for black holes, it's a very low value. So I think people have studied the impacts of spin, and it does change the ejecta mass, but it's not dramatic. I think it's sort of, tens of percent, even for like very rapidly spinning systems. And people have also, the general thought is that these are produced in binaries where the neutron star has, had time to spin down by the time of the merger. So I'm not discounting this. I just think my guess is it's the secondary effect. But you're right. If you want to say there's extra parameters other than just the total mass, like you could also say, what is the magnetic field of the neutron star? So if you start adding hair to the system,
Sure.
I agree this gets more complicated. But my understanding though is that spin is not you can't stay tidally locked, for example, when they come close together. So the spin is usually not that dynamically important. But you're right, it should be thought about.
What kind of observations do you need to confirm that event is a source of our process? For instance, you said that giant flare is like confirmed as like our process, but I'm just like wondering if you could go back to that argument.
I mean, to me, they're confirmed just because there's, no one has come up with another model that can explain what this MEV emission. And we think that this explains like three aspects of it, very naturally. And there was radio data, which also suggested mass ejection. So if you add up all the little pieces, which I'm usually doing in astrophysics, to me, it's compelling. It may not be compelling to particle physicists. So one thing we can hope to find is there are and they can become more prominent for lower velocity layers. There are more little bumps and wiggles here because this is a continuum formed from a bunch of different gamma ray lines. So if we have COSY or some future gamma ray satellite that could resolve these gamma ray lines, that I think would be more convincing evidence for people. I guess one would say, twist it around, I would say there's better evidence that this made our process arguably than 17817, which I think is also very strong evidence. It was also, I guess in this case you could say we didn't predict this, although we did make the light curves before we knew this observation was out there. But yeah, I think the thing would be to see gamma ray lines. And I think in 7807 and Kilonovae, it would be to see the optical, to see the atomic spectral line.
One last question. Yes. Yes.
Is that rate of magnitude giant flares on the top slide from the few that have been observed, or is it from like stellar population synthesis?
This is observed. So this is based on the 3 in the Milky Way plus some extragalactic flares, and it's highly dependent on the energy of the flare. So that's where a lot of the uncertainty comes in. Is we know one particularly energetic event we think produced this much material, but we don't know. There are more common, less energetic events, and we don't know if they produced as much or less. So that's the uncertainty. But this is measured.
All right, let's thank Brian again. So our second session today will be by Igor. Igor will tell us today about a lot of the observational counterparts of the stuff that we heard from Brian in the morning, and it will hopefully flow into the afternoon session where we will actually hunt real data streams for counterparts to gravitational wave sources. Right? Take it away.
Thanks, Kishali. A lot of counterparts. One. Just a quick outline of what I would like to tell you about. Surely observation of GW 17817. It's been almost 10 years now, so it's great. It's getting old, but we still love it. We still learn a lot from it, and I think as part of the school, it's good to know what was observed, so that you can also conduct future research in innovative manners, try to find more of what we know, and explore new regions of the parameter space as always. We'll have a bunch of slides, kind of going pretty quickly, maybe about other follow-up that was conducted after GW 17817. And the teaching part here is how can we extract science even from non-detection of counterparts? Try to bear with me. It's not as exciting as showing the latest and greatest discovery, but I hope it's going to be useful to you as well. And then we'll dive in a bit more on the technical side. How do we do kilonova searches, not just as a follow-up of a gravitational wave event or a gamma ray burst, but serendipitously during surveys. I will do it for ZTF and prospects for Rubin. And finally, I will conclude with the Rubin Target of Opportunity program. I don't think there will be time to dive into what's next. So, for the Roman Space Telescope. I will also not talk about kilonova associated with GRBs. We have to make choices. There's no time for everything, but it's surely a field we can learn a lot from, and I encourage you to go check out the relevant papers. Also, if you're new to the field, you would like to get a big overview of what's been done so far. Last year, sometimes Matt, Nicole, and I put together a review article for observations of gravitational waves, searching for electromagnetic counterparts. Matt has an incredibly fresh style of writing, so I think it will be very pleasant reading after, of course, you read Brian's review on Kilonovae and you actually understand the physics. So we will not go into general relativity formalism, but just remember where everything comes from, right? We need this equation that match the metrics that govern space-time and motion space-time, energy, and in particular, the solution for this equation has this parameter h, which then, when massaged and taken into its scalar form in a dimensionless form, what we call the strain. That's the observable in gravitational wave radiation. Something to keep in mind is how the strain relates to delta L, where L is the length of your system. So delta L in this case is how much your system has to shift physically for you to make a measurement over the total size of the system. Strain is small, in the order of 10 to the minus 21. Keep that number in mind. And in fact, Einstein said that these three pulses in the fabric of space-time called gravitational waves will be so vanishingly small that humans will never be able to detect. Now, what's the first gravitational wave detector that actually was successful at telling us quantitatively the gravitational wave exists? Any idea? Not LIGO. What was it?
Some kind of pulsar.
Some kind of pulsar, yes. So we can actually use astrophysical objects as detectors. In particular, people were very lucky in finding a double neutron star system in which at least one of the neutron stars was a pulsar. So it was observed with radio telescopes and can be timed. And thanks to this timing, what they found out, Hoss and Taylor, the people who conducted this study, is that the period kept changing in a way that is incompatible with energy being conserved without any loss into deep space. So thanks to that, you can tell, yes, energy is being lost, and the deviation from the more Newtonian gravity prediction is perfectly in line with expectation from general relativity if you assume that the system loses energy via gravitational wave radiation. So this is how Hoss and Taylor got their Nobel Prize in 1993. It's been really fun to win a Nobel Prize. And maybe some of us will get there one day. And I think it's even better when you see that your prediction initial data keep being confirmed in a more and more spectacular manner as time passes and more precise measurements are then possible. When you want to make a more direct observation of gravitational wave, well, you may use a Michelson and Morley sort of experiment, which was initially conceived to measure the ether, because there can't be void in the universe. And of course, as we all know, the ether was not proven to exist, at least not in a measurable manner, but the LIGO and Virgo detectors were built using a very similar principle, powerful lasers, and interferometry of these powerful lasers. But what was the strain that we have to measure for gravitational waves? Anyone remembers? 10 to the minus? 21. How long is one arm of LIGO, more or less? A couple of kilometers. Okay, please pair up a group of 2 or 3, tell me how precise you have to be in your measurement to detect gravitational waves. Keeping in mind that the strain is equal to delta L over L. L is the size of our system. We need to calculate delta L. Go.
But still, yeah.
All right, let's bring it in. Any volunteer? Well, what's the measure that you came up with in meters or your favorite small units?
-17.
10 to the minus 17. Anyone else got something radically different? Minus 17, minus 18 meters. That's meters, I imagine you wanted to say? Yes, very small. How big is an atom? What's the classical radius of an atom?
Angstrom.
Angstrom. 10 to the minus 10 meters. So this is way smaller than the size of an atom. It's actually even smaller than the size of the nucleus of an atom. I think it's important for us to appreciate how precise the LIGO and Virgo experiments need to be to do what they're doing. But they managed. I think all of you know these plots, but the first direct detection as opposed to indirect detection with the pulsar. Direct detection of gravitational waves. Some of you already have a T-shirt with this gravitational wave signal. I've seen a bunch. Brian, do you have a T-shirt?
No, but thanks, stickers.
Yeah. Stickers count. And once again, yeah, the participants in the GW business, you may also win a Nobel Prize. And one was awarded at record speed in 2017, was it? Yeah, 2017, I think, for gravitational wave discovery. But the signal we're most interested in today is the one that Brian already mentioned, a different signal compared to the binary black hole mergers that were detected until then. It was a much longer duration. It stayed for a longer time, at least in the frequency range at which the LIGO detectors were sensitive to. You have frequency here, time on the x-axis, and the color tells you the intensity of the signal. I was there. I was a student. I was in Australia, and look at what time you need to be awake to attend international calls if you live in Australia, and if you're a dedicated student who doesn't like sleeping and life. It was about midnight. While we were waiting for a call to start with my supervisor, we're using Skype, we're chatting at the time. You know what you had. It was not that long ago, but technology evolves really fast. Jeff, my advisor, were not very excited because he thought I was referring to some information coming regarding some swift follow-up of another binary black hole merger that happened just before, very interesting. But they already knew it all, of course. So I said, this is something new, something huge, coincident detection. Between what? Gravitational wave signal and the gamma ray burst. This is very strong proof, very strong hint at least, that something energetic is happening in the universe. And one of the beauty of it is that if you put together localization information from the gravitational waves and from the gamma ray burst, then you can have an even better map of where the source may be located in the sky. In this case, the Fermi GBM gamma ray burst monitor localization is in dark blue. You have this kind of banana shape, which is the initial LIGO localization. Actually, the initial one was basically all sky because there was a glitch in one of the two detectors. So localization was basically inexistent. But with time, they managed to clean up the signal and come up with a small region in the order of about 30, 32 square degrees. It's very small. I'll show you later a comparison with more recent events. And this allowed astronomers to go look for a counterpart, and indeed a counterpart was found. The method that was used was galaxy targeting. So because the source was so close, about 41 megaparsec, the volume that you have to probe within 30, 50 square degrees and change, actually not that large. It's a small shell if you consider the standard deviation that you have from the distance probability distribution of the gravitational wave signal. So if you go one galaxy at a time, you may actually be even more efficient than tiling the entire region with wide field telescopes. And that's how the SWOPE observatory managed, people using the SWOPE telescope managed to identify for the first time the counterpart, AT 2017 GFO, SA17A. It has been given a lot of names. Let me refer to it as just GW17A17 moving on. It was truly finding a needle in the haystack, however. In this animation, you have galaxies from the 6DF survey in a 3D rendering, and you will see where the host galaxy of GW170817 lies. The resolution is not the best, but you can tell that in context, there is quite a job that astronomers have to do to be able to localize the correct host, which is needed then to establish the distance with accuracy, do the study of the environment, and do cosmology. And this is how small the localization of GW1717 was compared, thank you. All my slides will be dark, so yeah. Oh my, everyone's gonna fall asleep so badly. Thank you. This is compared to all the previous detections of binary black hole mergers. What you may notice, even just from RGB snap at different times. So August 17 was the first day of 11 hours, more or less, from the gravitational wave signal. You can compare that image with image acquired a few days later. What can you observe? It's redder and dimmer, essentially. It faded and it changed color. This is, I mean, nothing really, it's not obviously as beautiful an image as the one from Hubble that Brian showed before. It's just close to my heart because it was in our paper collecting all the Australian-led observations. 14 instruments actually observed it, and we collated in one paper, and this image was taken with the SkyMapper telescope, and you can tell, yes, on the August 18, there is a source transient where there wasn't before. The reason why I'm showing that image is just to introduce this other animation, which is just a time elapse. Again, in RGB images, real data acquired with the SkyMapper telescope. And as the video progresses, you can tell the calendar days moving. 18, 19, 20 of August, 21, 22. It's so immediate to see what's happening. Dimmer, and redder. And now you even know why this is happening from an astrophysical viewpoint. What about the spectra? Spectra are so important, especially in transient astronomy, in optical astronomy more as a whole. Optical, typically, broadly speaking, is wavelength shorter than 10,000 angstrom, okay? This part. What you have in the optical is a continuum. You don't really see lines. However, if you go in the infrared, especially at later times, you see these very broad structures form. These, we believe, they're a blend of many lines thanks to all the transition that happen when you have very high opacity. Well, you have very high opacity because of all the transitions. It's actually, I think, conceptually the other way around. And also you can tell the shift in color, right? If you consider the continuum, it's peaking in the optical, in fact, at early times, probably the UV, if we manage to take data even sooner, and later on peaking towards the near infrared. Same data with a nicer visualization. And you can tell how rapidly it fades away, feature starts forming, and the peak of the SED of the continuum shifts towards the near infrared compared to the earlier times.
Wait, sorry, Igor. What is the time zero for this? Is this the time zero of discovery of the optical transient or time zero of the GW event?
I don't know, but I should double check that. I guess is from the GW event. Like if I was producing it, that's how I would do it. Because I think it makes more sense physically if you want then to go back and compare observations with your models. But yeah, we can double check Elena's paper.
Is the way that line moved as it traced out the different spectra physically motivated, the bright one that swept downwards?
Are you asking about the?
Yes, so like you your first shape, and then that bright line in that animation moved down into the second spectra that was taken. The way it moved down, was that physically motivated, or was that just
I think it was a somewhat of an interpolation of the two. I'm not sure. This is again more for like the pleasure of the, more for the public, I think, to be appreciated. It's not trivial, you know, to make a smooth transition from one to the next to the next. I think they actually did a very good job. But I think those were real spectra, so probably they were not modeled from one to the next. Although there are models that now try to go for each and every step in between, even where we don't have data. Anyone has any other questions before we move on? Okay. If not, well, I will not dwell into explaining a little bit what the picture we have now is, but for sure we did observe the short and hard GRB, even if we were off axis, right, somewhere between 20 and 30 degrees, depending on which study you consider, off the center of the cone of the jet. And the optical kilonova indeed reflects, we believe, the same type of physical picture that Brian and others have brought forward, pioneering the field. I would have not used the word crackpot, but I'm glad that the universe gave you.
That was the nucleus of this field. The astronomers are more open-minded. So.
We like original ideas, especially when they turn out to explain very well what we observe. So thank you for that. Another representations done by another theorist in Italy, Stefano Scienzi. I like it because he's an artist as well. Have you ever seen this?
I have. I like it.
Yeah,
it's
so
much prettier.
It's pretty. It's all done in watercolors or whatnot. and you can see the various components. So the torus of ejecta that may be responsible for the redder component that we observe, more lanthanide, neutron rich, the bluer kilonova that we expect coming from winds that are dominant towards the polar regions. And then the cocoon, this structure to the jet that was also observed in this case on top of the prediction for the jet itself. So there was just a bit more to it. Something not quite moving at relativistic speed, but still moving faster than the rest of the ejecta and bluer in color. What about the R processes for which we learned so much about? So thanks to all the theory and the simulations, people managed to match or fit the best that they can the models, in this case, the red curve, and to the observations, the black curve. So this already gives us a hint. Yes, maybe the heaviest elements were formed because, like Brian mentioned before, if you need to add all those components, you need to add this redder lanthanide-rich component at later phases to be able to get spectra that would match up what we're observing in the near infrared. Some probably even stronger conclusions to an extent can come from observations in the infrared. Again, that's where we expect the heavy elements to be the best observable. And I will not go through all of this because Brian already did. So we are targeting, in particular, elements that are in the second and in the third abundance peak. In particular, those heavier than the atomic mass number of 180. We do not have direct evidence of that. People will say we observed that. I wouldn't say it's a lie, but it's not entirely correct. We are observing some quantities and we're comparing our models to observations, assuming that there is also production in the second and third phase. And this is what you obtain in this plot when you plug in the infrared late time photometry, here the black data points on the bottom right. I think this is the bolometric luminosity of GW17 at 17. And all the dashed lines that you see are models for different values of the electron fraction. The ones fitting the best are the one with the lowest electron fraction, or close to the lowest. And that's what tells us, yes, the matter, the ejecta must have been neutron rich. Yes, there are the conditions for the heaviest element production. And what about direct measurements of, well, finding elements in the spectrum? Like I said, they're probably big blends of many lines. It's not just, oh, that's obviously H alpha, that's obviously iron 2. That's not the case, or at least we didn't think so. However, there is work, for example, this one by Watson and colleagues, that they claim that some of these broad features may actually be ionized strontium. And also, I think Kento Otokezaka published a paper recently providing evidence that there could be also tellurium in the spectrum. So if you're interested, go dig in this paper, see what else you find there, or maybe you can bring forward your own idea of what we're observing there. Counterpart was also found in the X-rays, in the radio. My understanding is that primarily observations can be explained as synchrotron. So this coming directly from the afterglow of the GRB. There are some claims that this late time flare from the Kilonovae is also observed. I think the debate is still on. But, I don't know if more observation of this event will clear the matter, but hopefully more observations in the future can help us understand how solid those detections are.
I think there's a claim that there's some claim that the X-ray is continuing to behave, and some that it's flattening, but it's very, very hard.
Yeah, I know, and people have very strong opinions on it. So we'll take a neutral stand. It will be.
I think there's something to learn, whether there's enough photons in the to measure. Probably good.
Yeah. X-ray astronomy is hard. You count photons one at a time. What else was observed? Superluminal motion. Now, in the radio, if you manage to have a long enough baseline, meaning various distances between the components of your radio array, you can get exceptionally good spatial accuracy in your observations. Thanks to that, goes some milliarcosecond precision of the radio observations. Something, I mean, not surprising nowadays, but maybe that back at the beginning, I think, of radio astronomy was something unexpected. You see the source moving. The disturbing fact is that it moves at a speed faster than the speed of light. That's not okay. But then if you take special relativity class, then you will learn that it is okay. It's just a relativistic effect for which the observer can measure velocity faster than the speed of light in a certain reference frame if you have a relativistic jet coming at you at an angle. However, it means there was a jet. And I think actually maybe I should have not sold it to you as a done deal. Oh yeah, you observed the jet, no problem. Because in fact, despite observing the GRB at the beginning, it was not quite clear if the jet was partly suppressed, was fully successful, meaning it managed to break through the circumstellar material like a normal GRB. This gave conclusive proof that material is moving at highly relativistic speed. Something curious, they managed to do that, not just in the radio with the work led by Giancarlo Ghirlanda and Kunal Muli, but also with Hubble Space Telescope, thanks to its very good spatial resolution. It's another work that I think it was led by Kunal Muli again, with Wenbin Liu and I think another person. We'll check it out.
Igor, why wouldn't presence of a gamma ray burst indicate a jet?
So I personally have not looked into this very much. I think it was not clear from the beginning how off axis it was, and also if the observations that we see come from the structure of the jet or is the main beam, and if that would mean that it's at least partly suppressed and it's like a choked jet. It's typically that was already disfavored as a scenario, but we need still conclusive proof.
The gamma ray signal observed in 1708-17 is pretty smooth, and therefore it could be explained also by a relativistic shock breakout, which means that you could have a jet that's kind of trapped inside the ejecta and doesn't fully break out, but just kind of blows up a relativistic or kind of quasi-spherical structure.
Thank you very much for the addition and explaining the main reason of the controversy. Any other questions?
I just wanted to mention that another thing we've looked at regarding the relativistic motion of the source in early times. So we've shown that the lack of a cooling break in the synchrotron spectrum at early times could only be explained if the source was moving at least slightly relativistic with a gamma of 2 or 2.5 or something, because the presence of the hot and bright kilonova would have caused cooling of the hot electrons by inverse Compton at early times unless the source is expanding rapidly. So this was an independent constraint from the superluminal motion that was only seen in later times with VLBI. So just a comment.
Anything else? Well, if not, let's move now more towards finding kilonovae. So this is once again the beautiful compilation of data points that Ashley Wheeler has published. It's quite striking. Once again, we're talking about a transient that is rapidly evolving, rapidly reddening. The peak magnitude, this is in the apparent magnitudes, but in absolute magnitudes, it's about -16. So for people who like more physical units, does anyone remember? That was mentioned multiple times in the previous talk. How many ergs per second, more or less? 41. Less than that, more 41. Several times 10 to the 41 ergs per second. That's fine, it's small. Typically what we have 10 to the 51 or so is for GRBs, is for supernovae, is for much more energetic sources. And I mean, that's okay in that it explains the physics. It's not okay if you're an observer, because it makes it hard to do our job. It makes it hard to make discovery happen. And this is, for example, how the light curve in one band, I think it's either G or R band, they're fairly similar in this case, of GW170817 compares to some of the standard classes of supernovae. Fainter peak, rapid evolution, difficult job. Once again, I will not expand on the GRB plus kilonova association, but if you are a multi-messenger astronomer, you may not want to ignore GRBs. In fact, you may want to observe GRBs that also behave as a fast transient, even faster than kilonovae, and that they may have a late time bump, particularly visible in the infrared, that may indicate the presence of a kilonova. And that's, if that's not a supernova, then chances are that the progenitor is a binary neutron star system or neutron star black hole merger. Now, generally speaking, how do we do gravitational wave follow? So, LIGO and Virgo collaboration issues an alert that now includes the chirp mass, by the way. It's beamed, so it's very coarse, but I think we have some idea of the chirp mass. It gives us spatial information, maps that tell us the probability for each pixel in the sky for the presence, from the origin being there of the merging system. So what we do, we then either do galaxy targeted searches or synoptic searches using wide field telescope, and we typically find a lot of transients. A lot can be a few dozens, a lot can be thousands, especially in the year of Rubin is going to be interesting. And maybe, just maybe, one of them is a kilonova or an afterglow. So what do? If you're lucky enough that the sources are bright, there's telescope time, and you manage to observe rapidly enough, you can do spectroscopy. So you can compare the spectra you acquire with what you would expect from a kilonova. So in the optical, it's basically a black body. If you see bright emission lines, it could be explained as hydrogen, for example, that's probably not a kilonova. This is how we have a bit more conclusive classification of a transient compared to just using photometry. And where are we at when it comes to the timeline for the LIGO and Virgo detectors? we're inching close to the end of 04, the fourth observing run. If you think that GW17 at 17 was found towards the end of 02, yeah, it's been a minute. So hopefully we'll find something very soon, and then plans for the future currently are uncertain. They depend on the funding situation, so we'll not expand too much. Now I will go very fast. So don't try to follow all the details, okay? Just the general concept. Otherwise you go crazy, especially given that it's almost lunchtime. All three, plenty of events, no counterpart was found. However, there was the second binary neutron star merger that is likely to be such, at least, found in gravitational waves. We did follow up with ZTF. The squares that you see are the 47 square degrees field of view of ZTF. But even doing all the searches we could in the northern hemisphere, also this part was close to the sun, was very hard to observe. We identified 15 promising candidates. We did spectroscopy or deep photometry for all of them. None of them match what we expect from Kilonovae. Look also how different the map is from GW17 at 17. And yes, this is what we typically have to play with nowadays. So a nearby loud event can lead to much better localization as well. And recently, this paper was published presenting all the observations for this event. It's a lot. People really tried hard to make this observation happen, but nevertheless, no counterpart was confidently identified. Here I'm just putting some references for more work we have done as part of the ZTF collaboration, following up a the second BNS merger, neutron star black hole mergers, and then trying to draw some conclusions from non-detection on the kilonova luminosity function. So how many are brighter than a certain magnitude, how many are on the fainter end. A work that I co-led in this case, the southern lobe observation of what we believe may be a neutron star black hole merger that just happened to be right behind the galaxy. Not good. So something has to keep in mind. If your region of interest is behind the galaxy, you have extinction, crowdedness, you can still do the best you can, but it becomes quite challenging. So what's one way to do science, even with a non-detection? Like in that case, we said that for this much probability that we observe, when I say probability, I mean the integrated probability that I infer from the sky map issued by the Ligon-Virgo collaboration. For those areas, given our limits, so in this case, the down-looking triangles, we can reject some models. In this case, on the left is the model for GW17 at 17. The reason why you see these bands is because we're not sure how distant it is. Just have, again, some error bars given by LIGO. And on the right, you see a plot in which we tweaked the parameters of the models. So maybe there could be that the kilonova was there. We're just not sensitive enough. For example, if the kilonova was particularly red. So if the lanthanide fraction was very high, or the electron fraction is very low, like you can say the thing in both ways. And I'm going to use this other example, much better localized, that happened on August 14th in 2019. Actually, we thought we found it. Usually, do you remember this guy?
I took that spectrum.
I know. It was a very difficult data reduction. And from the beginning, this helium line was just buried in the noise. The evolution was good, getting redder pretty fast. And then Kilonovae is too good at his job. So he broke our heart, and especially made us throw away the overleaf that we started writing. You can probably recognize the format. We thought we had it, but
Can I ask a quick question?
yes.
I want to emphasize something to observers, which is you can form helium in a neutron star merger ejection. So no, I mean, I'm assuming this event showed that was not the only evidence that it had a helium.
I can't remember for this one. But this, I mean, to me, this looks like type 1.
Okay.
Yes,
Okay.
yes.
Okay, look, I'm not saying you can produce that particularly strong
Yes,
out. I just want to emphasize that there's always a little bit of helium in addition to our process. It might be a few percent by mass. So it's not obvious, but it could be excited by radioactivity. So there's actually some debate, this Astronomical feature, that it potentially could have been a helium. I don't know if it can produce emission. All I want to say to the observers is be a little careful.
Just almost every time I interact with Brian, either talking or via email, you make me think of something like I have to go back to look again at the data to see if we're looking for something different and only looking something different. So well, thank you for the input. One other way to do science in this case, instead of just making your plot and say you can reject GW 17817, which by the way was particularly bright compared to expectations. But you can create a bunch of parameter spaces. This is one example. We also have another one, say with opacity, linking back to Brian's talk. In this case, I think I cut the y-axis. I apologize. Oh my, that's unreadable. I'm very sorry. This is something that copying and pasting from a previous presentation didn't work well. Here is ejecta mass on the y-axis. This is 0.3. I remember that much. So 0.3, 0.5, so on and so forth. So what you can do with non-detections, assuming certain distances, in this case are represented by different colors, you can say, okay, I am confident that in this region of the parameter space, there was not a kilonova. So you remain with some allowed region for where to play around with interpretations and models. What about O4, the current observing run? Well, there has been at least one case of interest, a neutron star black hole merger, which happened on February 6th, earlier this year. This was followed up, I think, again, by a large number of telescopes. Here, I'm going to report observations from a few, like the Dark Energy Camera, SOAR, Wendestein, and once again, a lot of upper limits. Now, what's your guess? Which upper limits are going to be the most constraining?
The earliest ones? The early ones?
The early ones. Any other thoughts?
R-band, right?
R-band, so would be the blue ones. Yeah, could be these ones. It's actually not obvious. In the previous plot that I showed, this one, the best constraints come from day 3, Z-band deep imaging. But yeah, in this case, they come from the earliest part because it's deeper, it's sooner, we can place better constraints. Although this was done galaxy targeted over a large volume, the probability is very small. But once again, we can play this game. Which models can we reject? Yes.
So this plot you showed with like ejecta mass versus observing angle, that's the Kilonovae emission that sensitivity is based off of?
Yes, correct. So basically what we're doing is we fix some parameters in the model grid. We play with 2 in this case, which is the orientation and the ejecta mass. And basically, if our observations manage to constrain that model, it will go in the disallowed region. If it's not deep enough, it will go in the allowed region.
So does this take into account like extinction effects along the line of sight, or is this? Okay, so I was gonna say it's like, Kilnoa is isotropic, so I wouldn't expect such a strong dependence on observation angle, but if it's.
Well, depends who you talk to, but if you check out the model grid by Mattiabulla, it looks like there is a pretty strong dependence on the viewing angle. And I think also multiple model, yours as well, right? For sure, Duncaisens also predict the kilonova not quite to be isotropic. Maybe some component, yes, but the presence of a blue component may be appreciated only from the more polar angles.
Right, but I just would naively expect, I mean, yeah, the ejecta mass is like subrelativistic, right? So I mean, sure, you have different geometry dependence on the different components, but each component should emit isotropically, right?
Well, if you have a fast, high opacity tidal tail, even if you don't see it in emission, you know, if it's expanding faster than some of the polar, you know, from the equator, it might block some of the polar stuff. So there are ways just geometrically without relativistic speeds for like lanthanide material to block non-lanthanide material. So I think that's what gives rise to some of this. Exactly. But that may not have been the red component we saw. It might have been present. It can absorb even if it can't emit. But anyways, yeah.
But in fact, if we knew in advance the viewing angle, we could also adjust observing strategy accordingly because of that. For example, using bluer filters, if you know you're closer to an axis, and maybe change strategy in other cases. But just find it. I think typically that's how you want to go for.
Are people planning to do that? Like if you see a coincident gamma ray burst?
I think so. I think in that case, you want at least to have one observations in G band, because also the physics you can do and you can infer from the initial part is the one that is probably more debated at the moment. So there are more models, say from radioactive decay, shock cooling, maybe this neutron precursor that Brian was referring to. So there is, I think, a lot of interest in probing that early phase, especially in the bluer bands. But again, if you kind of know already that you're not going to see it, you may just want to optimize your observations differently, going immediately towards the redder bands. Any more questions before we switch gear? We go into talking about how to find kilonovae in survey. No? Well, the power of serendipity. So ZTF has been run. I mean, I talk about ZTF because I'm part of ZTF, because it's one of the main robotic surveys that are active nowadays and release public alerts you all can fetch and process and do science with. So that's why I'm going to use mainly ZTF as a reference point here. But a survey like ZTF finds hundreds of transients per night. It releases in the order of, like we said the other day, about 300,000 alerts every night. So you find a lot of real astronomical transient that you can then classify. And in these animations, all the dots you see are spectroscopically classified supernovae. It's a big data set. Just the latest data release has more than 61 million images. And almost, what is it, 1 trillion source detections? Not too bad. That's why you need observers at CCA. It's a big data problem. Just saying. You're visiting programs. It's nice to be in this in New York. What would a kilonova look like in ZTF data? Spoiler alert, we have not found one yet. We found a ton of candidates, but we hammer them. When we find them, we go spectroscopy, photometry, X-rays, radio. We try to get to the bottom of it. So far, we don't have any confident transient that is a kilonova, but this is what you may expect to see. A handful of data points, even assuming a decently good cadence. Colors being red or becoming red, and non-detection preceding and following the several detections you have. This is what we're after. And in fact, this one I still don't know what it is. It still bugs me. It's one that I found during archival searches for Kilonovae and ZTF data back in 2020. Look at this light curve. So it's red. There is upper limits about 5 days before the first detection. The color is pretty red, close to pink. And then it drops like a rock. We have only our band observations here and nothing afterwards. We went with Keck to observe, but still we couldn't find a likely host galaxy. We just couldn't get much information, even going deeper than 26 magnitude. I still don't know what this is. I'm gonna play around with models, maybe for relativistic explosions. In the paper has a link to force photometry. You can check it out. But this is what you're doing. You have a handful of data points. You have to separate them from all known classes of transients, and then do modeling, do follow-up, try to get as much information as you can. However, this made it very clear to us, doing archival searches is really nice, but we need something to work in real time. There are multiple programs within ZTF and in general in the community at large that do real-time detection of fast transients. Something that we made quite routine now is finding afterglows without GRBs. This is, I think, a very interesting field on its own, because you can probe low Lorentz factor explosions. You can probe potentially slightly off-axis cases. Still no kilonova, unfortunately. Shock cooling, also for whoever likes the early stages of supernova evolution. This is what we do. Look for something that rises quickly, fades away quickly. And want to bring that into Ruby. So a little bit of a takeaway, once again, how do you do science with non-detection? It's kind of a bit harder, paradoxically. You have to really tick all the boxes, more than if you have a slam dunk discovery. So what we did in this case is a Gantt chart with rates for binary neutron star mergers that you can infer in different ways. For example, in cyan color gravitational waves. In yellow, orange, you can see constraints from the optical, assuming that all kilonovae look like GW17 at 17, which is false. We don't know, it's not the case. You have to make some assumptions. And actually, we calculated rates for a whole bunch of models in the paper. The constraints we obtained are less than 900 per gigaparsec cube per year. But this was 2022, I think, in the end. So what I think where we are now is in the order of 300-400 events per gigaparsec cube per year, if you assume a constant luminosity function for kilonova. Start pushing to the lower end, which unfortunately is in agreement with what LIGO is not observing nowadays, or at least not at the rate we were hoping for. What about Rubin and SST? Well, Rubin's just starting now the science validation. Transients are found. There are a couple of papers that we put in archive last week. We're curious to give them a look. Can talk to me, talk to John, who's in the paper. The Harvard group also published a paper for transients in this initial release of Rubin data. But what are we going to do with Rubin as LSST, the legacy server space and time? So using what now we know are generous rates of, I think I use 800 events per gigaparsec cube per year, you can have more than 300 kilonovae in your data. What does it mean? You have photons in at least one image coming from a kilonova. Kind of my personal battle is that this is the wrong number to quote, because you do nothing with a pair of array and deck anywhere in the sky at a distance you don't know. Especially, of course, if it's not associated to a multi-messenger or multi-wavelength event. How many can you recognize as a fast transient? Serendipitously. That's kind of, to me, the more interesting question. And of course, numbers drop, several, up to a couple of dozens, maybe. So now we know that probably the rates are lower than 800 per gigaparsec cube per year, but the cadence has improved a little bit, not by that much, but my personal guess is that we would be pretty lucky if we find 1 or 2 kilonovae per year during LSST.
So this, sorry. This rate estimate is based on these like 2017 like kilonovae, right? But Brian also talked about this diversity of kilonovae. So has anyone thought about refining this rate estimate by kind of considering this broad range of different types of kilonovae you might be able to get?
I have. Not just me, there are also other papers, in particular one by Christian Setzer, who's based in Stockholm. They studied even deeper study of the expected population of kilonovae. In our group, we took a slightly different approach in that we know so little about the diversity of kilonovae that, in my opinion, everything falls within the error bars. So I wouldn't stress too much with that part of the modeling at the moment until we have more examples. But what we did, we took some extreme cases. Once again, you have a grid of models and you go, okay, what's 1 kilonova that is particularly bright? Oh, you need a lot of ejecta mass. Maybe a pretty high electron fraction. And that will give one extreme. And then you can go the other extreme. And we tried to get, that's where also these numbers come from, is accounting for some variety of kilonova models. I think predictions now are far from accurate because we're still in small number statistics. But every time there is a new grade of kilonova, we like to throw it in and make better prediction thanks to the work of theorists.
Maybe I can make 2 points. One is exactly what you said, which is if you think that mergers are the dominant source of the art process, then you need basically the ejecta mass times the rate to be some quantity. So technically, if we knew, which we don't know, the number is precisely enough, there's not infinite wiggle room. You can't say I'm going to make 1,000. You can't make a really high rate of high ejecta mass kilonova, so that should trade off a little bit. But we don't know those numbers good enough, well enough. The other point I'll make is what I said in my talk, which is that if you look at the galactic neutron stars that actually merge in a Hubble time, they actually do have pretty uniform properties. But then we know that there are things like 0920 which are whatever it is completely different. So I wouldn't be surprised in the end if there is a class of like 170817 like events that aren't terribly different. And then there's, as you said, a huge diversity. But I don't think it's crazy to think of 17817 as a prototype, because it could be that a lot of binary neutron stars, for whatever reason, have similar properties. If you look at the galactic population, that's my only point. I think it's worth entertaining that as possible.
How many of these, like between 350 and the kind of 3 to 30-ish? Mm-hmm. So what kind of, how many of them do have a couple data points where you could potentially detect them, given a better detection algorithm?
Thank you for the question. In that's kind of the dominant factor is how you observe first, and second, how do you make your selection? What we did as a community at large, so more like 2,000 people contributed in various capacity, not just for the Kilonova science case, for all science cases of Rubin. Probably you remember all the papers I mentioned a couple of days ago for optimizing the survey strategy. What we did is to create metrics. A metric, you can think about it for transients as a selection criteria. We in our team developed probably 5 or 6 metrics for kilonovae. For example, one is at least one detection. One is at least two detection. One is at least two detection in two bands, so that you can say maybe something about the color. The one that I trust the most, based on experience with ZTF data, what actually allows me to do follow-up, I want to do the science now, I don't want to wait for Ruby, is finding something that is evolving fast. That's by far the best way to discriminate between a strong Kilonova candidate and anything else. So yes, you can definitely get different numbers depending how you select your transients, but also we always have to work with just a handful of data points. And this is actually a fairly good cadence for Rubin standards. That's even worse than that. So we will see how it works out. All right, kind of
one question. So that was my question about the previous one. This is not the Rubin cadence, right? Which
this was one example from an old set of 20 different cadences. This is not the latest by far.
Right. Okay, so do you know what the number is if you took the actual Rubin cadence, which is?
Yeah, I think Christina Andrade in Minnesota did it with a more recent one. Numbers are surprisingly similar. You just lose in one way, you gain in another way, but we're still in the order of several per year at most.
I just want to clarify, so the 332, you're saying these are detections you can make with LSST, just with LSST data, even given their cadence?
Correct. So this is without any active triggering of the telescope, just based on the observations as part of the wide fast deep survey.
So presumably we could do a little bit better by like overlapping between ZTF and LSST and improving that cadence rate.
Yeah, and for that reason, ZTF started now a program that has been announced also as an astronaut last week, for which we will observe the equatorial regions, so where you have overlap with Rubin, every night in 3 bands. In the area, I think is about what, 10,000 square degrees, something like that. So you have daily 3-band observation with ZTF, plus you will have more sparse but deeper observations with Rubin. So combining this data set will be key to make discovery.
For Rubin discovered Kilonova, is the assumption that you're still going to have to get really deep spectra, like when this thing is faded a bit and you're taking spectra at 25th mag? Or is the world of Rubin Kilonova going to be a lot of only photometric detections? Like this is the main figure on a paper?
Well, a magnitude 25 spectrum is either probably 2 nights of Keck non-stop, or maybe GWST. You're not going to be able to do that for maybe more than 1 event every year or 2, if an insane amount of resources are thrown at it. So this will not be the norm. That's why all the development of algorithms that can intelligently separate kilonova candidates from supernovae and other type of transients will become more and more relevant. It's really the only thing we'll be able to work with in most cases. Hopefully, multi-wavelength information will also add to what we know. In these cases, for serendipitous discoveries, it's very unlikely that there will be gravitational wave detection. These are distances typically in the order of 1 gigaparsec. So like in this case, still we're very, very bright compared to the detection limit. It's 400 megaparsec, is already further than LIGO and Virgo can currently reach, and at the very edge of after the next upgrade. Be a difficult game, but that's also why we need to work so much in synergy with theorists that can help us understand what is it that we observe with the little information that we have available. Any more questions about serendipitous discovery of Kilonovae? Well, if not, a few words about the TO program. First of all, what does TO mean? What does it stand for? Target of opportunity. That means you're stopping everything you're doing and you just slew your telescope to a region of interest. And I've been TO'd once this semester. It never happened before. It hurt. It's on this telescope. Sore. I was triggered. What's going on? So I apologize to everyone who doesn't do transient science or doesn't have, is not used to this. But it happens pretty often, actually, that telescopes allow for a little bit of time to be devoted to these opportunistic observations that may be the only way to make some transient science. Rubin wasn't quite born with the target of opportunity program in mind, but there has been a strong push for it from the beginning. Some of the people that pushed the most in the earlier phases, captained by Raf Margutti, are the ones, at least some of which are displayed in this slide. This is a white paper that we brought forward to the Rubin project in 2018, basically saying we need target of opportunity to be integrated in the Rubin plans, mainly to do gravitational wave follow-up. Rubin, 10 square degrees, field of view, great depth, exceptionally good follow-up machine for the discovery of Kilonovae and afterglows. How did that evolve? Well, we tried now, first of all, the good news is that the observatory was very receptive and that they decided to allocate up to 3% of LSST time for TOs. This is already a great win. They're interested in doing groundbreaking science, so there was not a lot of pushback, maybe from other programs that are really not interested in multi-messenger and need uniformity. For them, it's a problem. So we're trying to balance everything out, right? So what we did last year is to be even more inclusive scientifically. We brought everyone interested in any type of TOs at Berkeley. We had a workshop out of which we came out with a very long report. I think it's more than 60 pages long, and now it's undergoing peer review. It's a lot, but the beauty of it is that it collects gravitational wave astronomers, people who want to do neutrino astrophysics. You can follow up neutrino alerts that are typically localized to 1 to several square degrees. People interested in potentially hazardous asteroids. You may have an asteroid that may or may not hit the Earth. You really want to follow that up. Check out what it's doing. So these are three of the main science drivers for the Target of Opportunity program. So what we did is actually design strategies for the follow-up of gravitational waves and for the follow-up of these other sources of interest. So I will ask 1 minute, 2 minutes, based on the observational properties of GW 17817, the variety of Kilonovae, how would you design the program? Say if you can use Rubin to do follow-up of gravitational waves, how often would you observe? With which filters? And please don't give the answer that Salafia, a theorist, gave me some time ago. When I asked that question, he responded, I want one data point at 25 magnitude every 10 seconds for 2 weeks in a row. And then he said, I'm a theorist. So try to think something sensible, like you need to save as much time as possible, but maximize the science. Think about it, discuss with your neighbors.
Do you want to come and contribute on the server? Like,
I'm just like, why, why not just look at the black hole binary merger error? But it's not a random. And also, you're optimizing based on atmospheric mass, right? Which is not always going to be where it's light source.
But again, I should say, okay. So the problem of talking with someone like Brian is that they immediately hit the point. When I go there and I go and ask, so what would you do? He obviously answer a question with a question. What area are you considering? What probability region? And that's exactly an extremely important point of, not quite contention, just something to keep in mind. You can't design a strategy if you don't know how much of the sky you're looking at. You need to look at 1,000 square degrees or 2 square degrees. You need 1 pointing per night, or do you need 100 pointings just to cover the area of interest? If you're working on a budget, that makes a major difference. So from this was what, 2022, especially members of the Transient and Variable Star collaboration came together, writing a paper that is somewhat an evolution of the white paper. What we did is start designing strategies in terms of these pie charts in which you put all the filters you would like to use. Keep in mind, why is this unrealistic? On each pie, why each pie is wrong?
It's either U or Z.
Correct. Almost
Y.
correct.
Sorry.
The problem is the filter width is actually not it's not 6 filters, but only 5. Nevertheless, the idea here is throw the kitchen sink at it, every color you can. And our idea at the beginning was, okay, how can we balance everything out for exceptionally well localized events, better than say 20 square degrees? try to observe 3 times on the first night in all bands. This, I mean, prefer this very wishful, you know, but hey, if you don't ask for a lot, you're not, typically you get less than what you ask. Let me see it that way. Something more reasonable probably is the minimum strategy in which you still have multi-band photometry more than 1 epoch on the first night. This can enable detection rapidly, detection and I mean an identification. Plus, if we're lucky, will allow us to do that bit of interesting astrophysics regarding the initial few hours from the kilonova, from the merger. And then, of course, depending also on the type of source, in this case was a binary neutron star or a neutron star black hole merger, models tend to predict a possibly redder, brighter signal. Again, it depends a little bit which models you use, but you may want to tweak a little bit your strategy, right? So you not always, for example, you may be able to use all the filter wheel. You may want to select only a couple of filters. In this case, G and Z. We'll talk maybe in a minute about why. And what about binary black hole mergers? They may have a counterpart, maybe prompt, maybe later times. The real answer is that we don't really know on which time scales those counterparts evolve. Hours, days, weeks, months. So the approach we're suggesting is just make sure you do some TOOs at the very beginning. Don't miss out on the first hours. And then make sure the observations happen sort of in a log-spaced sort of thing. A couple of filters get colors.
How disruptive are the preferred and the minimal TOOs in terms of like the time that they take out of the night?
Yeah, we did some calculation and then even conducted simulations. It can be like a factor, literal factor of 10 different.
Yeah, I was going to ask what, so is the TO program, sorry, this is a bit backing out, but in terms of how black hole mergers will be prioritized, I mean, I'm guessing you're going to just wait until you have a really good set. I mean, if you looked at every black hole merger, that would already be your few percent, I assume. So you have to select which of those you're going to go after. So I'm assuming it's going to be better localized ones or weird ones. Or...
Extremely well localized, possibly with high chirp mass. Those are the ones that I think people working on this type of modeling agree are the most likely to have a luminous counterpart. Also, you want to save time. You want to use Rubin well in terms of like using the whole potential of the wide field of view, something that we were kind of forced to say in the report. So this is not yet the report. This is still the paper from a couple of years ago. But it's to say if a counterpart is identified, we will stop observing. That's not great because you really like the multi-band, extremely well calibrated photometry you get from Rubin. But if you don't do that and use for single pointing, people scream at you, and also that would give rise of justifying also follow-up for a whole lot of other science cases that many of us really love and we can do great science with, but at the moment are considered out of scope, once again, because we want to use Rubin as a discovery machine, not a characterization machine. It's something we do, heavy-heartedly, but it's necessary.
How do you determine if a counterpart's observed and it's not just like a supernova within the localization region that has the properties you expect?
Primarily via spectroscopic follow-up. Or if you have, say, you're lucky enough that you have a gamma ray burst detected by Swift while you have a LIGO merger, and at some point you have sub-arcominute localization, then use Gemini instead. So something can go equally deep or even deeper with without disrupting LSST in the meantime for everyone else. Remember, the community is about 4,000 people. People interested in multi-messenger about 1 to 200. So 3% is already not too bad. My hope is that LSST will finish in 10 years. And after that, I don't think they will dismount the telescope straight away. So it can go wild there, I hope. We will see.
So I was just going to add that I think this counterpart identification problem, I think you're safe from that because you'll never be able to convince people that something is the counterpart, even with this. I've seen this game from the outside. Like you see a featureless spectrum, like someone says the core collapse supernova, someone says the kilonova.
Is GW1707, okay, is AT 2017 GFO a kilonova?
Only after a week of observations. Before a week, you couldn't convince anyone. This is from actually looking at the process. Yes, yes.
Gotta play the game, man.
So are these timescales for follow-up chosen with like specific or possible counterparts in mind? Or I guess like what counterparts would you expect on these timescales following up?
Do you mean for the binary black hole
Yes,
case?
yes.
I think the idea was probe different timescales. So there are some theories more regarding possible jetted emission, in which case you want observation the first couple of nights. Most of the models, I think actually someone here can give a whole lecture on them, are more related on binary black hole mergers that happens with massive black holes in thick AGN disks. You have Bondi accretion, you have dragging of the gas, shocks, and is there anything you would like to add about that?
You can also have interactions between a jet from a jetted remnant and the actual disk gas. It's going to shock the disk gas. And this is kind of more so to introduce, there's multiple ways to produce some type of like thermal shock. Yeah, and we can chat on it.
So this plot, this is an updated version. This actually came out from the report. So not a bit less wishful, a bit more practical. As you can tell, the strategy now, if you look at the top scale, that's days, maybe it's a bit easier to read. So the first night, you try to have, in the best cases, at least 3 sets of observations. And keep going for at least 2 or 3 nights. Now, Kishley was actually making an excellent point. It's very hard to photometrically distinguish a kilonova from anything else. And even if you have a spectrum, then that may not be enough. But we just can't go on forever. We may convince the observatory to do that in exceptional cases, but not if we want to carry out a systematic experiment over dozens of mergers. And you can see, yeah, the number of filters has dropped to 3 in the first part, from 5 and then 2. Can anyone guess why 3 is a decent number? What do you want to do with 3 filters? Or can you measure? Not too much, but you can measure something.
If the emission is thermal or non-thermal?
Thermal and non-thermal, yes. You can do just enough modeling of the SED to get a rough idea of the temperature and whether it may not be a non-thermal emission, because once again, we're going after afterglows as well. And then why do we want to keep going with the G and I band and not with the other filters? Any ideas?
Distinct colors, right? You want the furthest possible filters.
Exactly. So you want filters that are far from each other in wavelength range, in center wavelength, I should say. Keeping in mind, kilonovae redden very rapidly, and this is one of the best diagnostics we have. However, beware, supernova shock cooling looks an awful lot like kilonovae. That's what we learned from CTF and other surveys. So it's complex, but in that case, spectroscopy actually can typically help, especially if you see these hydrogen lines in emission. This is coming from models like best fit of GW 17 at 17. You can tell that as time progresses, you have a larger and larger gap. Especially look in the top line is G minus Z. However, we prefer I band typically because it can allow us to get much deeper than Z band. It's just the throughput and the response of the detector is better. So the good news is that it's not all about simulation anymore when it comes to GW follow-up with Ruby. To the left is from another paper, from the paper I mentioned before, from 2022. On the right, that's real. This is a GW follow-up that happened, that is still going. I think more images were taken last night. I still haven't checked my Slack. I feel so much better not having checked Slack by noon. I've never done it before. But these are pointings of the telescope acquired in the follow-up of a binary black hole mergers, and this occurred on July 29, so just last week. So things are happening, the TO program is becoming reality, and on top of that, once again, as a community, we're pushing for the science verification survey to build more templates where the LIGO and Virgo detectors are more sensitive. For that reason, they added to the survey this semi-square patch. This is only in I band. We just have to pick one band. What do you pick? I band is a bit more ubiquitous when it comes to Kilonovae observations. So if anything of interest happens in this area, it will be a little bit easier for us to do follow-up, image subtraction, and get products. I don't think I have time to go through for Roman. Just mentioning Roman Space Telescope will be great for extremely, when I say extremely well localized, I already said it before, this is more extremely well localized, like in the order of 5 square degrees. You can still do something amazing there, but even during the survey that Roman will conduct, in synergy with Rubin, you're going to have colors and depth. Rubin arrives to the dashed black line as depth. This is what Roman can do. If I find Kilonovae, I'll trash it too. So yesterday I concluded with a quote. I think I'll do something similar today. Some of you were very nice yesterday, asked me, what did you do over the weekend in New York? Did you go to see a Broadway show? But I know they're amazing, I really do. But I think this is more my jam. Linkin Park was in town. I hope all of you at least have heard of them. I know they're okay. But so I got a last minute ticket and just rushed to New Jersey to listen to them. The show was incredible. I loved it. It made me smile listening to the lyrics. You know, sometimes songs talk to you. For example, when singing Burn It Down, he starts by saying the cycle repeated, like explosions broken. That's obviously a supernova. All that I needed was the one thing I couldn't find, clearly referring to a kilonova. But see also, in the end, we have some hope in the universe that more will happen. And yeah, I'll conclude here and happy to take questions. Oh, I haven't seen it.
Question?
So a conference a while ago, and someone was like, "Oh, could LSSD try and like preferentially observe places that are within the gravitational wave lobes?" Did any of that end up materializing?
Yeah, that's actually how
that
path
region
was chosen.
Okay.
For the templates. But then in the end, Rubin will observe, we'll do the gravitational wave follow-up in the footprint of the main survey. So you can add up those observations to the main survey, so that limits disruption. for everyone else. It's about, 18, 19,000 square degrees.
How are the TORs going to be approved? Are there any cases in which there might be like automatic follow-up, like if you have another like small localization gravitational wave TB, or like most of them going to be approved case by case?
Yeah, so it's largely TBD. It's going to be semi-automatic. There will be an algorithm that tells you go, no go, but there will also be a committee that will make immediate decisions to approve the go or even to stop observations from happening. For example, say if there is clear communication from LIGO that an event is not real. In that case, we will want to retract it, or if there is any other of such issues. And the call for this committee has come out like 2 days ago, 3 days ago. So if you're interested, or you know someone who may be interested, check it out and volunteer to be part of this decision committee for the next 2 years.
Any other?
So you focus mostly on TOO from gravitational wave side, but as we saw with 17917, there may be, for the right orientation and distance, a GRB, and so some small subset of GRBs, other than the ones that are magnetar flares, could be, these low luminosity things that are fairly close. So is there plans to filter through like GRBs that might be associated with the nearby universe and to trigger on those, or is there any connection to the sort of gamma ray triggers, I guess?
Not at the moment. Part of the reason is just focus your efforts to at least obtain the program to happen. The other reason is because gamma rays typically are either very well localized immediately, like subarc minute, or is thousands of square degrees. It's one or the other at the moment. Unless you have then IPN localization. For
Are
now,
you referring
it's
to
not,
BAT versus like GBM?
for example, yes, but even Konos, like that's
okay. I didn't think GBM was that bad. Okay, yeah, it's definitely not. Yeah, it's not.
GBM is hundreds to thousands.
Okay.
So in short, at the moment, there is no plan for that. But every year we will reevaluate priorities, especially when the GW detectors are down. Maybe there will be more room for this other type of searches.
I think people are talking about, CubeSats that will give better sky localization.
We really need to update depending on the facilities online at any given time.
Okay, I think we should break for lunch. All right, let's thank Igor again.